The ocean you know is a lie, not because it does not exist, but because it is only the latest draft of a story that has been written and rewritten over hundreds of millions of years. Beneath the waves that crash against our shores today lies a memory, an echo of a world so profoundly different, so spectacularly alien, that if you were to dive into it, you would not recognize a single rule by which life operates. There was a time, stretching across tens of millions of years, when the seas were warmer, wider, and more dangerous than anything the modern world has ever produced. A time when the oceans swallowed continents, when predators grew to lengths that would dwarf the largest sharks alive today, and when the very concept of who eats whom was never settled, never fixed, never safe. This is the story of the Cretaceous Oceans, a chapter in Earth's history that ended not with a whisper but with the most catastrophic event life on this planet has ever endured. And from that ending came everything that followed, including the seas we swim in now. Please let us know in the comments where you are watching this history video and what time you are watching it, and be sure to subscribe to the channel for future videos. To understand the Cretaceous Oceans, you have to first understand what the world looked like when they existed. And to do that, you have to abandon almost every assumption you carry about geography, climate, and the shape of the Earth itself. Because the Cretaceous period, which stretched from roughly 145 million years ago to 66 million years ago, was a world remade. The continents were not where you expect them to be. The climate was not what you imagine it to have been. And the oceans were not the deep, cold, stratified bodies of water you have been taught to picture. They were something else entirely. Let us begin with the land, because to understand the sea, you must first understand what the sea replaced. During the Cretaceous, the supercontinent known as Pangaea had already been breaking apart for millions of years. The landmasses that would eventually become the continents we recognize today were in motion, drifting apart on the backs of tectonic plates, opening vast new seaways between them. Where there had been a single enormous body of land surrounded by a single enormous ocean, there were now fragments, pieces of a puzzle being slowly pulled apart by the restless machinery of the Earth's interior. And as those pieces separated, the ocean rushed in to fill the gaps. This was not a subtle process. The rifting of continents created enormous basins, and those basins filled with seawater. New ocean floors were being generated at mid-ocean ridges at rates significantly higher than what we observe today. And when new ocean floor is created rapidly, it is hot. Hot rock is less dense than cold rock, and less dense rock sits higher. This means that the ocean floor itself was elevated, pushed upward by the heat of its own creation. And when the ocean floor rises, the water that sits on top of it has to go somewhere. It goes onto the land. This is one of the most important facts about the Cretaceous world, and it is one that most people never learn. The oceans were not confined to the deep basins we associate with them today. They spilled over onto the continents. Vast, shallow seas, sometimes called epicontinental seas or eparic seas, covered enormous portions of the landmasses. These were not narrow strips of coastline or modest bays. These were inland oceans, hundreds of kilometers wide, stretching across the interiors of continents, connecting ocean basins that today are separated by thousands of kilometers of dry land. Imagine standing on what is now the interior of a great continent, 1,000 kilometers from the nearest modern coastline, and looking out over warm, shallow water that extends to the horizon in every direction. That was the Cretaceous reality. The sea levels during this period were among the highest in all of Earth's history, perhaps 200 meters or more above present levels, and the result was a planet that was, quite simply, more ocean than land. The ratio of water surface to land surface was dramatically different from what we experience today. The Earth was a water world, not in the science fiction sense of a planet with no land at all, but in the very real sense of a planet where the oceans dominated the surface to a degree that has no modern parallel. And these were not cold oceans. The Cretaceous was a greenhouse world. Atmospheric carbon dioxide levels were far higher than they are today, perhaps 4 to 6 times higher, possibly more. There were no permanent ice cap at either pole. The polar regions, while cooler than the tropics, were temperate, forested, and free of the massive ice sheets that define our modern poles. This absence of polar ice had profound implications for the oceans. Without ice caps, there was no mechanism for the formation of the cold, dense bottom water that drives modern deep ocean circulation. The thermohaline circulation, that great global conveyor belt of cold water sinking at the poles, traveling along the ocean floor, and rising in warmer regions, either did not exist in its modern form or operated in a fundamentally different way. What this meant was that the deep oceans were warmer, not warm by the standards of a tropical beach, but significantly warmer than the near-freezing temperatures found in the modern deep sea. Bottom water temperatures during the Cretaceous may have been 10 to 15 degrees Celsius warmer than they are today. This is an extraordinary difference. It meant that the entire volume of the ocean, from surface to floor, was warmer. The temperature gradient between surface and deep water was less extreme, and this had cascading effects on everything from ocean chemistry to the distribution of life. Warmer water holds less dissolved oxygen. This is a simple physical fact, but its biological implications are enormous. In a world where the entire ocean was warmer, oxygen levels in many parts of the water column were lower. This created conditions ripe for the development of what scientists call oceanic anoxic events, periods when large volumes of ocean water became so depleted of oxygen that most aerobic life could not survive in them. These events were not constant, but they were recurring features of the Cretaceous Oceans, and they left their mark in the geological record in the form of thick layers of black, organic-rich shale, the preserved remains of all the organic matter that sank to the oxygen-free bottom and was never decomposed. We will return to these anoxic events later because they are a crucial part of the story. But for now, the important thing to understand is the stage upon which the drama of the Cretaceous Oceans was played. It was a stage defined by warmth, by vastness, by shallow seas that covered the land, by the absence of ice, by altered ocean circulation, and by a chemical environment fundamentally different from what exists today. It was, in every sense, a different world, and in that different world, a different kind of life evolved. The creatures that inhabited the Cretaceous Oceans were not simply larger versions of modern marine animals. They were products of a different set of evolutionary pressures, shaped by a different environment, occupying ecological roles that do not map neatly onto anything we see in today's seas. To understand them, we need to first understand the ecological framework in which they existed, because that framework was itself unlike anything in the modern ocean. In the oceans of today, we are accustomed to thinking in terms of relatively stable hierarchies. There are apex predators like great white sharks and orcas that sit at the top of the food chain. Below them are various levels of secondary predators, then primary consumers, then the producers at the base, the phytoplankton and other photosynthetic organisms that convert sunlight into the organic matter that fuels the entire system. This hierarchy is not perfectly rigid, of course. There are complexities and exceptions. But in broad terms, the modern ocean has a structure, and that structure is relatively stable over ecological timescales. The great white shark does not worry about being hunted by the fish it eats. The orca does not lose sleep over the possibility that a school of herring might gang up and devour it. There is a directionality to the flow of energy and the relationships of predation, and while individual animals may die of many causes, the hierarchy itself persists. The Cretaceous Oceans did not work this way, and this is perhaps the single most important conceptual shift you need to make in order to understand what life was like in those ancient seas. The Cretaceous marine ecosystem was characterized by a fluidity, an instability, a constant negotiation of power and position that has no real analog in the modern world. There was no single apex predator that reigned unchallenged. There was no fixed top of the food chain. Instead, there was a web, and every creature in that web was simultaneously predator and potential prey, hunter and hunted, dominant in one moment and vulnerable in the next. This was not chaos, it was not random. It was a system, but a system governed by different rules. The rules of the Cretaceous Ocean favored adaptability over dominance, flexibility over specialization, the ability to shift strategies over the ability to perfect a single one. And the fossil record, that extraordinary archive of ancient life preserved in stone, provides us with direct, tangible evidence of how this system worked. Consider what it means to find a fossil of a predator with its prey still inside it. This is not common in the fossil record, but when it happens, it is extraordinarily informative. It tells us not just what an animal ate, but how it ate, how large its prey was relative to its own body, and sometimes how that meal went wrong. In the Cretaceous Oceans, we have multiple examples of this kind of fossil, and what they reveal is a world where predators routinely attacked prey that was almost as large as they were, where the act of eating was itself a gamble, and where the line between a successful hunt and a fatal overreach was razor thin. This is not how modern apex predators typically operate. A great white shark does not usually attack prey that is 90% of its own body length. An orca does not swallow a seal that fills its entire body cavity. These modern predators have the luxury of selectivity, of choosing prey that is small enough to be consumed safely and efficiently. The Cretaceous predators, many of them, did not have that luxury, or perhaps more accurately, the competitive pressures of their environment were such that caution was itself a risk. In a world where every meal might be your last, but also where failing to eat aggressively enough might leave you too weak to survive the next encounter, the calculus of predation was different. The margin for error was smaller, the stakes were higher, and the result was an ecosystem where violence was not just common, but was woven into the fabric of daily existence in a way that even the most dangerous modern oceans cannot match. Let us talk about one of the most remarkable creatures to emerge from this environment. The story encapsulates everything we have been discussing about the nature of Cretaceous marine life. Its name is Xiphactinus, and if you have never heard of it, you are about to meet one of the most extraordinary fish that ever lived. Xiphactinus was a bony fish, a ray-finned fish belonging to a group called the Ichthyoctids. It lived during the late Cretaceous, roughly 90 to 66 million years ago, and it inhabited the warm, shallow seas that covered much of the world during that time, and it was enormous. Adult Xiphactinus could reach lengths of 5 to 6 meters, with some estimates suggesting individuals may have grown even larger. That is 15 to 20 feet of fish, a creature longer than most modern great white sharks and built with a very different set of design priorities. Xiphactinus was built for speed. Its body was elongated and streamlined, tapering from a broad, powerful chest to a narrow tail stalk that ended in a large, deeply forked caudal fin. This tail design is one we see in modern fast-swimming fish like tuna and mackerel, and it serves the same purpose, the generation of rapid, sustained thrust. The deeply forked tail is hydrodynamically efficient, allowing the fish to swim at high speeds without wasting energy. And Xiphactinus needed that speed because its hunting strategy was based on rapid pursuit. The head of Xiphactinus was large and equipped with a gaping jaw filled with sharp, pointed teeth. These were not the broad, crushing teeth of a fish that feeds on shellfish. They were not the tiny, filter-feeding teeth of a fish that strains plankton from the water. They were the teeth of a predator designed to seize and hold fast-moving prey, to grab and swallow, to close on a struggling fish and not let go. The jaws could open wide, very wide, because Xiphactinus hunted by engulfing its prey, by overtaking it in a burst of speed and then swallowing it, often whole. And here is where the story of Xiphactinus becomes truly remarkable and truly illustrative of the Cretaceous marine ecosystem, because we have fossils, extraordinary fossils, that show us exactly what happened when Xiphactinus ate, and what they show is astonishing. The most famous Xiphactinus fossil, and one of the most famous fossils in all of paleontology, was discovered in the chalk deposits of a great inland sea. It is a specimen of Xiphactinus audax, approximately 4 meters long, and inside its body cavity, perfectly preserved, is the nearly complete skeleton of another fish called Gylicus arcuatus. This Gylicus is about 1.8 meters long. That is nearly half the length of the Xiphactinus that ate it. Nearly half. Imagine a predator swallowing prey that is almost half its own body length, whole, in a single act of engulfment. The Gylicus is curled inside the body cavity of the Xiphactinus, its bones still articulated, still connected, still in their proper anatomical arrangement. It was swallowed intact. It did not go down easily, and it appears that the effort of swallowing this enormous meal may have killed the Xiphactinus itself. This fossil, sometimes called the fish within a fish, is not merely a curiosity. It is a window into the ecology of the Cretaceous seas. It tells us that Xiphactinus was an aggressive, ambitious predator that regularly tackled prey at the very upper limit of what it could physically consume. It tells us that the act of predation in these ancient oceans was not a clean, efficient process, but a brutal, dangerous struggle that could end badly for the predator as well as the prey. And it tells us something about the competitive environment in which Xiphactinus lived, because an animal does not evolve to take such enormous risks with every meal unless the alternative, the conservative approach, the cautious strategy, is itself too dangerous. If you do not eat enough and eat fast enough, something else will eat you first, or something else will eat the prey before you can get to it, or you will simply starve in a sea full of competitors. Xiphactinus was not alone in this regard. It was one of many large predatory fish in the Cretaceous seas, and it shared its environment with a dizzying array of other hunters. There were other ichthyoctids, some nearly as large as Xiphactinus itself. There were large sharks, including species of the genus Cretaceous, sometimes called the Jinsu shark for the sharpness of its teeth, a predator that could reach 6 meters or more in length and whose teeth have been found embedded in the bones of other large marine animals, including Mosasaurs. There were marine reptiles of various kinds, from small, darting forms to enormous, top-tier predators. And there were the creatures we will discuss at length shortly, the Mosasaurs, the marine reptiles that would come to dominate the late Cretaceous seas in a way that no single group had dominated them before. But before we come to the Mosasaurs, it is important to linger a moment longer on the world that produced Xiphactinus, because the details of that world tell us things that the broad strokes cannot capture. The seas in which Xiphactinus hunted were not deep oceans in the modern sense. They were shallow, warm, and teeming with life. The water column was productive, with abundant phytoplankton feeding vast populations of small organisms, which in turn fed larger organisms, which in turn fed the great predators at the upper levels of the food web. But the productivity of these seas was not uniform. It varied with the seasons, with ocean currents, with volcanic activity that could alter water chemistry, and with the periodic anoxic events that could render large areas of the ocean uninhabitable. The chalk deposits in which many Cretaceous marine fossils are found tell us something important about the nature of these seas. Chalk is a type of limestone composed primarily of the microscopic shells of organisms called coccolithophores, tiny single-celled algae that float in the upper layers of the ocean and produce intricate plates of calcium carbonate. When these organisms die, their shells sink to the bottom and accumulate in vast quantities, eventually forming thick layers of chalk. The existence of extensive chalk deposits from the Cretaceous tells us that coccolithophore populations were enormous during this period, that the surface waters were warm and productive, and that the accumulation of organic material on the sea floor was prodigious. It also tells us that the seas were, in many places, shallow enough for this fine-grained sediment to accumulate without being swept away by strong deep water currents. These chalk seas were the arena in which the great drama of Cretaceous marine life played out. They were not the deep, dark, mysterious oceans of the modern abyss. They were sunlit, warm, and relatively shallow, often less than a few hundred meters deep, sometimes much less. Light penetrated to the bottom in many areas. The water was often clear enough, at least at times, for predators to hunt by sight over considerable distances. But it was also subject to turbidity, to the stirring up of fine sediment by storms and currents, to blooms of microscopic organisms that could reduce visibility to near zero. The visual environment of these seas was dynamic, constantly changing, and the animals that lived in them had to be equipped to deal with that variability. This brings us to a topic that is easily overlooked but fundamentally important to understanding how Cretaceous marine animals lived and hunted: the role of sensory systems. Every predator in every environment in every era of Earth's history is defined by its senses. The ability to detect prey, to detect predators, to navigate, to find mates, to avoid obstacles, all of these depend on sensory input. And in the Cretaceous Oceans, the sensory challenges were significant. Vision was critical, but vision in these seas was not like vision in the open air. Water absorbs and scatters light. Even in the clearest tropical seas, visibility is limited compared to what is possible in air. And in the Cretaceous Eperic seas, conditions were often far from clear. Sediment plumes, phytoplankton blooms, suspended organic particles, all of these could reduce visibility drastically. An animal that relied solely on keen eyesight in perfectly clear water would have been at a serious disadvantage much of the time. The eyes of Cretaceous marine animals, as reconstructed from fossils, show a range of adaptations to this challenge. Many of the large predatory fish had large eyes relative to their body size, suggesting that they relied heavily on vision, but needed to maximize light-gathering ability in conditions of reduced illumination. The Mosasaurs, as we shall see, had eye structures that suggest sensitivity to a broad range of light conditions, from the bright, dappled surface waters to the dimmer regions below. But vision was only one part of the sensory toolkit. Many Cretaceous marine animals would have possessed lateral line systems, those arrays of pressure-sensitive receptors that run along the bodies of fish and some aquatic vertebrates, detecting vibrations and changes in water pressure. In murky conditions, the lateral line becomes the dominant sense, allowing a fish to detect the movement of other animals, the approach of a predator, or the struggling of nearby prey, even when visibility is zero. Sharks, both modern and ancient, possess an additional sensory modality: electroreception, the ability to detect the weak electrical fields generated by the muscle contractions of other animals. This sense, mediated by specialized organs called ampullae of Lorenzini, allows sharks to find prey that is hidden, buried, or invisible in murky water. Cretaceous sharks almost certainly possessed this ability, and it would have given them a significant advantage in the variable conditions of the Eperic seas. The interplay of these sensory systems created a hunting environment of extraordinary complexity. A predator might detect the presence of prey first through its lateral line, sensing a distant vibration in the water. It might then close the distance using that pressure sense, orienting toward the source of the disturbance. As it drew closer in conditions of sufficient light, vision might take over, allowing the predator to identify the prey, assess its size and condition, and plan its attack. In the final moments of the approach, electroreception for those animals that possessed it might provide the fine-grained, close-range information needed to make a precise strike. And throughout this process, the prey would be using its own senses, its own lateral line, its own vision, its own instincts to detect and evade the approaching predator. This was the reality of life in the Cretaceous seas. Not a simple world of big fish eating small fish, but a sensorily rich, tactically complex environment where every encounter between predator and prey was a contest of detection, evasion, speed, and strategy. And it was in this environment that the most successful group of marine predators in the late Cretaceous evolved, diversified, and ultimately came to occupy almost every major predatory niche in the world's oceans. We are talking, of course, about the Mosasaurs. The story of the Mosasaurs is one of the most remarkable evolutionary narratives in the entire history of life on Earth. It is a story of transformation, of a group of animals that began on land, returned to the sea, and in a relatively short span of geological time, became the dominant marine predators on the planet. It is a story that challenges many of our assumptions about how evolution works, about the constraints of anatomy and behavior, and about the relationship between opportunity and adaptation. Mosasaurs were reptiles. Specifically, they were squamates, members of the same order that includes modern lizards and snakes. Their closest living relatives are monitor lizards, the varanids, a group that includes the Komodo dragon. This means that the ancestors of Mosasaurs were terrestrial animals, land-dwelling lizards that walked on four legs, breathed air, and had no particular connection to the ocean. And yet, over the course of their evolutionary history, they became fully aquatic, spending their entire lives in the sea, giving birth to live young in the water and never returning to land. This transition from land to sea is not unique in the history of life. Whales did it, starting from small, four-legged, hoofed mammals and ending up as the largest animals ever to live. Seals and sea lions did it, retaining a partial connection to the land but becoming primarily aquatic. Ichthyosaurs, the marine reptiles that preceded the Mosasaurs by tens of millions of years, did it so completely that they came to resemble dolphins in body form, one of the most striking examples of convergent evolution in the fossil record. But the Mosasaur transition was remarkable for its speed and its completeness. The earliest known Mosasaurs, or rather the earliest known members of the Mosasaur lineage, appear in the fossil record in the mid-Cretaceous, roughly 100 million years ago. These early forms were relatively small, perhaps a meter or two in length, and they were semi-aquatic, likely spending time both in the water and on land, much like modern marine iguanas or semi-aquatic monitor lizards. Their limbs were still recognizable as limbs, with functional joints and digits. Their tails were long but not yet specialized for swimming. They were, in essence, lizards that had begun to exploit the resources of the shallow seas, but the transition did not stop there. Over the next 30 to 35 million years, the Mosasaur lineage underwent a dramatic transformation. The limbs shortened and flattened, becoming paddle-like flippers used for steering and stability rather than for walking. The tail elongated and developed a downward bend at its tip, supporting a large crescent-shaped tail fluke that provided the primary propulsive force for swimming. The body became more streamlined, more hydrodynamic. The skull became specialized for different types of prey, with variations in tooth shape and jaw structure that reflected different feeding strategies. And the Mosasaurs grew. They grew enormously. By the late Cretaceous, roughly 70 to 66 million years ago, Mosasaurs had diversified into dozens of species spread across every ocean on the planet. They ranged in size from relatively modest forms of 3 to 4 meters in length to absolute giants. Tylosaurus, one of the largest and most well-known genera, could reach lengths of 12 to 14 meters, roughly the size of a large bus. Mosasaurus itself, the genus that gave the entire group its name, was similarly enormous, with some estimates suggesting lengths of up to 17 meters for the largest individuals. These were not small animals dabbling at the edges of the marine ecosystem. These were fully committed, fully adapted marine predators at the very top of the food web. And yet, even for these giants, the Cretaceous Ocean was not a safe place. This is the point we keep returning to because it is the defining characteristic of the ecosystem. Even the largest mosasaurs bore scars of conflict. Fossil mosasaur bones have been found with bite marks from other mosasaurs, suggesting intraspecific combat, fights between members of the same species over territory, mates, or food. Mosasaur bones have been found with bite marks from large sharks, indicating that even these enormous predators were not immune to attack. And mosasaur stomach contents preserved in the fossil record show that they ate a staggering variety of prey, from fish and squid to marine turtles, other marine reptiles, and even seabirds. They were not specialists. They were generalists, opportunists, flexible predators that could shift their diet and their hunting strategy based on what was available and what was achievable. This flexibility is one of the keys to the mosasaur's success. In a world without a stable hierarchy, the ability to eat many different things, to hunt in many different ways, to operate at many different depths and in many different conditions was more valuable than the ability to do one thing perfectly. A specialist is vulnerable to changes in the availability of its specific prey. A generalist is resilient, able to switch to alternative food sources when conditions change. And in the Cretaceous Oceans, conditions changed constantly. The diversity of mosasaur body forms and tooth structures tells this story eloquently. Some mosasaurs had long, narrow jaws filled with many small, pointed teeth, ideal for catching fast-moving fish and squid. Others had shorter, more robust jaws with larger, more heavily constructed teeth capable of crushing the shells of ammonites and marine turtles. Some had intermediate tooth forms, suggesting a mixed diet. This ecological diversity within a single group of animals is analogous to what we see in modern mammals, where a single order can include herbivores, carnivores, omnivores, and specialized insectivores. The mosasaurs were doing in the Cretaceous seas what mammals would later do on land, filling every available ecological role, exploiting every available food source, and diversifying to fill every niche. But the mosasaurs did not exist in isolation. They were part of a larger community of marine reptiles that included other groups with their own specializations and their own ecological roles. Plesiosaurs, those long-necked marine reptiles so often confused with the popular image of the Loch Ness Monster, were still present in the late Cretaceous, though they were less dominant than they had been earlier in the Mesozoic. Sea turtles, some of them enormous, patrolled the warm shallows. Marine crocodilians, distant relatives of modern crocodiles but adapted to ocean life, inhabited some coastal and shallow water environments. And above the water, pterosaurs, the great flying reptiles, skimmed the surface, plucking fish from the waves. This was a world of extraordinary biological richness. The Cretaceous Oceans were not empty expanses of water with a few scattered predators. They were teeming, crowded, competitive environments where dozens of species of large predators coexisted, each carving out its own niche but constantly bumping up against the others, constantly testing the boundaries of its ecological role, constantly adapting to the presence and activities of its competitors. And at the base of this entire system, fueling all of this predatory activity, was one of the most productive marine ecosystems in the history of the planet. The phytoplankton of the Cretaceous seas, including the coccolithophores we discussed earlier, along with dinoflagellates and other microscopic photosynthetic organisms, produced organic matter in staggering quantities. This primary production supported vast populations of zooplankton, which in turn supported dense schools of small fish, which in turn supported the larger predators. The food web was long and complex, with many links and many pathways for energy to flow from the sun to the top predators, and this complexity was both strength and a vulnerability. A complex food web has many interconnections, which means that the loss of one species can potentially be compensated for by shifts in the populations of others. But a complex food web is also a system with many potential points of failure, many places where a disruption can cascade through the system and cause effects far beyond the initial disturbance. This vulnerability would eventually be tested in the most dramatic way imaginable. Before we come to that, we need to explore more of the creatures and the dynamics that made the Cretaceous Oceans what they were. Because this was not a world that can be understood through the lens of a few charismatic megaphons. It was a world of incredible diversity at every level, from the microscopic to the monstrous, and every level was important. Every level played a role in maintaining the delicate, shifting balance that characterized the ecosystem. Let us return to the predators for a moment and consider something that the fossil record reveals with uncomfortable clarity: the reality of injury and survival. Modern paleontology has moved far beyond the simple cataloging of species and the reconstruction of skeletons. We now have the tools and the expertise to read the stories written in individual bones, to detect signs of injury, disease, healing, and trauma that reveal the lived experience of ancient animals. And in the Cretaceous marine fossil record, those stories are abundant and vivid. Consider a mosasaur jaw with a healed fracture. The bone was broken at some point during the animal's life, perhaps in a fight with another mosasaur, perhaps during an encounter with particularly resistant prey, perhaps in a collision with a submerged object. The break was not immediately fatal, The animal survived, continued to eat, continued to swim, continued to hunt, and the bone healed, knitting itself back together in a callus of new bone growth that is clearly visible in the fossil. This tells us several things. It tells us that the injury was survivable, that the animal was resilient enough to endure the pain and the impairment and to continue functioning. It tells us that the animal was able to obtain sufficient food during the healing period, despite having a broken jaw, which suggests either that it had alternative feeding strategies or that it was tough enough to hunt through the pain. And it tells us that the Cretaceous Ocean was a place where such injuries were common enough that we find them repeatedly in the fossil record. Healed fractures are not the only evidence of past trauma. We find bite marks on bones, both healed and unhealed. Healed bite marks tell us that an animal survived an attack, that it was bitten by a predator or a rival, and lived to tell the tale, at least in the language of bone. Unhealed bite marks tell us the opposite story. The attack was fatal, or at least occurred close enough to the time of death that no healing had begun. We find pathologies, signs of infection and disease in bones that struggled to heal properly. We find evidence of parasitism, of organisms that burrowed into bone and left their traces behind. Every one of these traces is a window into the daily reality of life in the Cretaceous seas, and collectively they paint a picture of an environment that was relentlessly demanding, where survival was never guaranteed, where every day brought new risks and new challenges, and where the price of living was written in scars. This is not to romanticize the violence of the Cretaceous Oceans. It is to understand it. Violence was not an aberration in this ecosystem. It was a fundamental feature, a driving force that shaped the evolution of every species that inhabited it. The arms race between predator and prey, between competing predators, between rivals within a species, was constant and intense. It drove the evolution of speed, of armor, of sensory acuity, of behavioral flexibility, of size. Every adaptation we see in Cretaceous marine animals, from the torpedo-shaped body of Xiphactinus to the crushing jaws of the shell-eating Mosasaurs to the elaborate defensive structures of Ammonites, was forged in the crucible of this constant, unrelenting competition. Let us now turn our attention to the Ammonites, because they are a group that deserves far more attention than they typically receive. When people think of the Cretaceous Oceans, they usually think of mosasaurs, of giant fish, of marine reptiles with terrifying jaws. The Ammonites are often relegated to a footnote, pretty fossils to be collected and admired but not deeply considered. This is a mistake. The Ammonites were one of the most successful, most diverse, and most ecologically important groups of organisms in the Cretaceous seas. Their story is not just a story of shells and spirals. It is a story of evolutionary creativity on a scale that few other groups have ever matched. Ammonites were cephalopods, relatives of modern squid, octopuses, and the chambered nautilus. They had external shells like the nautilus, divided into chambers that could be filled with gas or fluid to control buoyancy. The animal itself lived in the outermost chamber, extending its tentacles and body from the opening of the shell to swim, feed, and interact with its environment. And their shells were extraordinary. The diversity of ammonite shell forms in the Cretaceous is staggering. The classic ammonite shell is a tightly coiled spiral, like a ram's horn, with each successive whorl partially enclosing the previous one. This form is common and is the one most people visualize when they think of ammonites, but the Cretaceous saw an explosion of variation on this basic theme. Some ammonites evolved shells that uncoiled, producing long, straight forms like the orthocones of earlier cephalopod groups. Others produced shells that were loosely coiled, with the whorls not touching each other, creating helical or even hook-shaped forms that look almost like enormous calcified question marks. Some evolved shells with elaborate ribs, spines, and keels that projected from the surface, adding structural strength and potentially serving as hydrodynamic aids, defense mechanisms, or display structures. Some evolved shells with complex, bifurcating ribs that created intricate surface patterns of remarkable beauty. The suture lines of ammonites, the lines where the internal chamber walls met the outer shell, became increasingly complex through their evolutionary history. In early ammonites, these suture lines were simple curves. By the Cretaceous, they had become fantastically intricate, with elaborate fronds and fractal-like patterns that trace the most complex curves found in the natural world. The function of these complex sutures has been debated for centuries. One leading hypothesis is that they strengthen the shell, allowing it to withstand the pressures of deeper dives. Another is that they increase the surface area of the internal chamber walls, facilitating more efficient gas exchange and buoyancy control. A third suggests they may have provided attachment points for the mantle tissue that secreted the shell. The truth of all of regardless of the specific mechanism, the increasing complexity of Ammonite suture lines over evolutionary time is a clear signal of ongoing adaptation and refinement of a group of organisms that was continuously exploring the design space of its own anatomy. The sheer diversity of Ammonite shell forms in the Cretaceous tells us something important about the ecological conditions of the time. Diversity in evolutionary biology is often driven by opportunity. When there are many different ecological niches available, natural selection can push populations in many different directions, producing a wide range of body forms and life strategies. The proliferation of Ammonite shell types in the Cretaceous suggests that there were many different ways to make a living in the Cretaceous seas, many different habitats and food sources and predatory pressures that favored different shell shapes, different swimming styles, different buoyancy strategies. The Ammonites were not a monolithic group doing one thing. They were a kaleidoscope of forms, each adapted to its own particular way of life, together forming a critical middle tier of the marine ecosystem. Ammonites were prey for many of the large predators we have discussed. Mosasaur stomach contents include ammonite shells. The teeth of some mosasaur species are specifically adapted for crushing ammonite shells, suggesting that ammonites were a significant part of their diet. Ammonite shells have been found with bite marks that match the tooth spacing of various predators. And some ammonite shells show evidence of repair, of damage that was inflicted during the animal's life and then healed over, suggesting that not every encounter with a predator was fatal and that the shell provided meaningful protection at least some of the time. But ammonites were also predators in their own right. Like their modern cephalopod relatives, they were active, intelligent animals with well-developed senses and the ability to capture and consume prey. They likely fed on a variety of small fish, crustaceans, and other invertebrates, using their tentacles to snare prey and their beak-like jaws to tear it apart. Their position in the food web was thus intermediate. They were consumers of smaller organisms and prey of larger ones, a critical link in the chain of energy transfer that connected the primary producers at the base to the great predators at the top. The ecology of the Cretaceous seas was not, however, solely a story of predators and prey. It was also a story of symbiosis, of commensalism, of parasitism, and of all the complex intertwined relationships that characterize any mature ecosystem. The fossil record gives us glimpses of these relationships, though they are harder to detect than the dramatic evidence of predation. We find fossils of marine organisms encrusted on the shells of ammonites, suggesting that the ammonite shell served as a substrate for other organisms during the animal's life. Barnacles, bryozoans, worms, and other encrusting organisms colonized the surfaces of ammonite shells, just as they colonized the hulls of ships and the shells of modern sea turtles today. This tells us that ammonites moved slowly enough, at least at times, to allow these organisms to settle and grow on their shells. It also suggests that the relationship was likely commensal, beneficial to the encrusting organism which gained a hard surface to attach to, and neutral or mildly detrimental to the ammonite, which had to carry the extra weight and drag. We find evidence of parasites in the internal organs and body cavities of fossilized marine animals, preserved as traces, burrows, and pathological changes in the bones and shells of their hosts. Parasitism is one of the most common ecological relationships in the modern world, with parasites outnumbering free-living species by a significant margin, and there is every reason to believe it was equally common in the Cretaceous. The Cretaceous Oceans were not a paradise. They were a world of constant biological interaction, where every organism was subject to exploitation by others, where the web of relationships extended far beyond the simple dynamic of who eats whom. Let us now consider the physical environment in more detail, because the creatures of the Cretaceous seas did not exist in a vacuum. They were shaped by, and in turn shaped, the waters they inhabited, and those waters were remarkable. The temperature profile of the Cretaceous oceans was fundamentally different from that of the modern oceans. We have already discussed the overall warmth of the Cretaceous climate and its effect on ocean temperatures. But the details are important because they determined where animals could live, how they could hunt, and how the ecosystem as a whole was structured. In the modern ocean, there is a sharp temperature gradient between the warm surface waters and the cold deep waters. This gradient, called the thermocline, acts as a barrier to mixing. Warm, light surface water floats on top of cold, dense deep water, and the two layers do not readily mix. This stratification has profound effects on the distribution of nutrients, oxygen, and life. Nutrients tend to accumulate in the deep water, where they are released by the decomposition of sinking organic matter. Sunlight, which is needed for photosynthesis, is available only in the upper layers. The thermocline separates these two resources, and much of the productivity of the modern ocean is driven by processes that bring nutrient-rich deep water up to the sunlit surface, such as upwelling along coastlines and in the open ocean. In the Cretaceous, the thermocline was weaker. The temperature difference between surface and deep water was less extreme. This had several important consequences. First, it meant that the deep water was warmer and less dense, which may have resulted in less vigorous deep ocean circulation. Second, it meant that the barrier to mixing was weaker, which may have allowed nutrients to be distributed more evenly through the water column. Third, it meant that the deep ocean was more habitable for a wider range of organisms, since the temperature difference between surface and depth was not as punishing. But the weaker thermocline also contributed to one of the most significant oceanographic phenomena of the Cretaceous, the oceanic anoxic events we mentioned earlier. With weaker circulation and warmer water holding less dissolved oxygen, large volumes of ocean water could become anoxic, devoid of oxygen, for extended periods. These anoxic events were catastrophic for the organisms living in the affected areas. Fish, marine reptiles, and other animals that relied on dissolved oxygen for respiration could not survive in anoxic water. They would be forced to flee to oxygenated areas or they would die. The result was a periodic reshuffling of the marine ecosystem, as anoxic events wiped out populations in some areas and forced survivors into closer competition in the remaining habitable zones. The geological record preserves the evidence of these events with stark clarity. The black shales that formed during oceanic anoxic events are some of the most distinctive and informative rock units in the entire stratigraphic record. They are dark because they are rich in organic carbon, the preserved remains of organisms that sank to the anoxic bottom and were not decomposed by the oxygen-dependent bacteria that normally break down organic matter on the sea floor. These shales are also the source rocks for many of the world's major petroleum deposits, a fact that connects the ancient Cretaceous oceans directly to the modern global economy in a tangible, if often overlooked, way. The occurrence of these anoxic events was not random. They were linked to changes in ocean circulation, volcanic activity, and the carbon cycle. Large volcanic events, such as the eruption of large igneous provinces, could inject enormous quantities of carbon dioxide into the atmosphere, enhancing the greenhouse effect, warming the ocean, and reducing its oxygen-holding capacity. At the same time, increased nutrient input from volcanic activity and weathering could stimulate primary productivity, producing more organic matter that consumed more oxygen as it decomposed. The result was a feedback loop that could drive the ocean into anoxia on a regional or even global scale. These events were not instantaneous. They developed over thousands to tens of thousands of years, and they could persist for similar periods. During an oceanic anoxic event, the marine ecosystem underwent significant stress. Species that were adapted to well-oxygenated conditions were pushed to the margins. Species that could tolerate low oxygen levels, or that lived in the surface waters above the anoxic zone, had a competitive advantage. The composition of marine communities shifted, with some groups declining and others expanding. And when the anoxic event ended, as conditions returned to more normal levels of oxygenation, the ecosystem did not simply snap back to its previous state. It recovered, but the recovered ecosystem was different from what had come before, with new species compositions, new food web structures, and new balances of power. This pattern of disruption and recovery, of crisis and adaptation, was a recurring theme in the history of the Cretaceous Oceans. The ecosystem was not static. It was not a single, stable state that persisted unchanged for 80 million years. It was dynamic, constantly shifting, constantly being perturbed by environmental changes and constantly adjusting in response. The creatures that thrived in this environment were not those that were perfectly adapted to a single set of conditions. They were those that were flexible, resilient, and capable of adjusting their behavior and their biology to meet new challenges. This is a lesson that the Cretaceous Oceans teach us about the nature of life itself. Stability is not the norm, change is the norm. And the organisms that succeed over the long run are not the ones that are best adapted to the present moment, are best equipped to handle the next moment, whatever it may bring. Let us now turn our attention to an aspect of the Cretaceous Oceans that is often underappreciated: the role of the physical structure of the seaways themselves in shaping the distribution and evolution of marine life. We have discussed the broad outlines of Cretaceous geography, the breakup of Pangaea, the formation of new ocean basins, the flooding of continental interiors. But the details of this geography were far more complex and far more consequential than a simple description of rising sea levels might suggest. The new seaways that opened as continents drifted apart did not merely provide more water for marine organisms to inhabit. They created new corridors for the movement of species, new barriers that isolated populations and drove speciation, and new patterns of ocean circulation that redistributed heat, nutrients, and organisms around the globe. The opening of a seaway between two formerly connected landmasses could have the same effect as the construction of a highway between two formerly isolated cities. It could allow the mixing of previously separated populations, the exchange of species between regions, and the establishment of new ecological relationships. Conversely, the closing or narrowing of a seaway could have the opposite effect, isolating populations, restricting the flow of ocean currents, and altering the climate of adjacent regions. The geography of the Cretaceous world was in constant flux, and this flux was a powerful driver of evolutionary change. Species that were once members of a single, widespread population could be divided into separate populations by the widening of an ocean or the rising of a mountain range on the sea floor. Once separated, these populations would evolve independently, accumulating genetic differences and developing new adaptations to their local environments. Over millions of years, these diverging populations could become distinct species, each adapted to its own particular niche. And if the barrier between them later disappeared, if the seaway closed again or the ocean currents shifted, these newly distinct species might come into contact again, competing, coexisting, or hybridizing in ways that further shaped the diversity of the marine ecosystem. The Cretaceous Oceans were thus not merely a backdrop for the evolution of marine life. They were an active participant in it, a dynamic, ever-changing environment that shaped the course of evolution through the physical forces of plate tectonics, ocean circulation, and climate change. The creatures of the Cretaceous seas were products of their environment in the deepest sense, and to understand them, we must understand the world that made them. One of the most fascinating aspects of the Cretaceous marine ecosystem is the way in which different groups of organisms rose to prominence and then declined, replaced by others in a constantly shifting pageant of ecological dominance. The Mosasaurs, for all their success, were not the first group of marine reptiles to dominate the Mesozoic seas. They were preceded by the Ichthyosaurs, which had been the dominant marine reptiles for much of the Triassic and Jurassic periods, and by the Plesiosaurs, which had been prominent throughout the Jurassic and into the Cretaceous. The Ichthyosaurs, those dolphin-shaped marine reptiles with their enormous eyes and their streamlined bodies, had been extraordinarily successful for over 100 million years. They had evolved from terrestrial ancestors, as all marine reptiles did, and they had become so thoroughly adapted to aquatic life that they gave birth to live young in the water, a fact confirmed by remarkable fossils that preserve mothers in the act of delivery. But by the mid-Cretaceous, the Ichthyosaurs were in decline. The reasons for their decline are debated, but it may have been related to the changing conditions of the oceans, particularly the oceanic anoxic events that disrupted marine ecosystems during this period. As the Ichthyosaurs faded, the Mosasaurs rose to fill the ecological roles they had vacated, a classic pattern of ecological replacement in which one group's decline creates opportunities for another. The Plesiosaurs persisted alongside the Mosasaurs in the late Cretaceous, but they occupied somewhat different ecological niches. The long-necked Plesiosaurs, with their small heads and their 4 large flippers, were likely pursuit predators of small fish and squid, using their long necks to reach into schools of prey and snatch individual animals. The short-necked Pliosaurs, the other main group of Plesiosaurs, were more robust predators with large heads and powerful jaws, but by the late Cretaceous, the largest Pliosaurs had already declined, and the Plesiosaurs as a whole were less diverse than they had been in earlier periods. The Mosasaurs, with their greater diversity and their more flexible feeding strategies, are the more successful group in the late Cretaceous Oceans. This pattern of successive dominance by different groups of marine reptiles is one of the most striking features of the Mesozoic marine fossil record. It tells us that ecological dominance is not permanent, that even the most successful groups can be replaced if conditions change in ways that favor their competitors. It also tells us that the marine ecosystem was resilient in the face of such changes, that the loss of one dominant group did not lead to the collapse of the ecosystem, but rather to a reorganization in which new groups rose to fill the vacated roles. The ecosystem was not dependent on any single species or group of species. It was a system, a network of interactions and relationships that could adjust and reconfigure itself in response to changing circumstances. But this resilience had limits, and those limits would be tested catastrophic Cretaceous period. Before we reach that, let us spend more time in the Cretaceous seas because there is so much more to see, so many more creatures to meet, so many more stories to tell. The large predators, the Mosasaurs, and the giant fish command our attention because of their size and their dramatic lifestyles. But the Cretaceous Oceans were full of organisms at every scale, from the microscopic to the colossal, and each of them played a role in the functioning of the ecosystem. Consider the marine turtles of the Cretaceous. Sea turtles are among the most ancient groups of reptiles, with a fossil record extending back to the late Triassic. By the Cretaceous, they had diversified into numerous species, some of which were enormous. Archelon, one of the largest sea turtles known from the fossil record, could reach lengths of over 4 meters from head to tail, with a flipper span of nearly 5 meters. It was a massive animal, armored with a bony shell but surprisingly vulnerable despite its size. Mosasaur bite marks have been found on Archelon bones, confirming that these giant turtles were prey for the top predators of the Cretaceous seas. Archelon and its relatives were likely omnivores, feeding on a variety of organisms including jellyfish, crustaceans, mollusks, and perhaps seaweed. Their large flippers, modified from the limbs of their terrestrial ancestors, were powerful swimming organs that allowed them to cruise over long distances, much like modern sea. And like modern sea turtles, they probably undertook long migrations between feeding grounds and nesting beaches, a behavior that connects them to the land even as they lived their lives primarily at sea. Consider also the sharks of the Cretaceous. Sharks are among the most conservative groups of vertebrates, meaning that their basic body plan has remained relatively unchanged for hundreds of millions of years. The sharks of the Cretaceous would have been recognizable to anyone familiar with modern sharks, though some species had distinctive features of their own. Cretaceous mantelli, the Jinsu shark mentioned earlier, was a formidable predator of the late Cretaceous seas. Its teeth were large, blade-like, and serrated, similar to those of the modern great white shark, and they were clearly designed for cutting through flesh and bone. Cretaceous grew to approximately 6 to 7 meters in length, making it one of the largest sharks of its time, and its teeth have been found embedded in the bones of mosasaurs, plesiosaurs, and large fish, confirming its role as a top predator. But Cretaceous was not the only shark in the Cretaceous seas. There were many other species, ranging from small, bottom-dwelling forms that fed on shellfish and small invertebrates to medium-sized predators that hunted fish and squid. The shark fauna of the Cretaceous was diverse and ecologically important, filling many of the same roles that sharks fill in the modern ocean. And like their modern descendants, Cretaceous sharks were characterized by their ancient, proven body plan, their keen senses, and their remarkable ability to persist through environmental changes that wiped out many other groups of organisms. The invertebrates of the Cretaceous seas deserve attention as well, because they formed the foundation upon which the entire ecosystem rested. We have already discussed the Ammonites and the coccolithophores, but there were many other groups of invertebrates that played critical roles. Rudist bivalves, for example, were a group of reef-building clams that were enormously important in the Cretaceous. Warm, shallow seas of the Cretaceous tropics, rudists formed extensive reefs that provided habitat for a vast array of other organisms, much as coral reefs do today. Rudist reefs were structurally complex, with towers and columns of interlocking shells that created a three-dimensional environment of crevices, tunnels, and overhangs. Fish, crustaceans, echinoderms, and many other organisms sheltered in and around these reefs, creating dense, diverse communities in the shallow, warm waters. The decline and eventual extinction of the rudists at the end of the Cretaceous would have profound consequences for the structure of marine ecosystems. Reef-building organisms are what ecologists call ecosystem engineers. They create physical structure that provides habitat for other species, and their loss can lead to a cascade of secondary extinctions as the species that depended on the reef habitat are left without shelter, food, or breeding sites. The loss of rudist reefs at the end of the Cretaceous was one of many cascading failures that transformed the marine ecosystem in the wake of the end Cretaceous extinction event. Echinoderms, the group that includes starfish, sea urchins, and sea cucumbers, were also abundant and diverse in the Cretaceous seas. Sea urchins in particular were common inhabitants of the shallow, chalky seas, their tiny, robust tests or shells preserving beautifully in the fine-grained sediments. Crinoids or sea lilies were less abundant in the Cretaceous than they had been in earlier periods, but they were still present, their delicate, flower-like forms anchored to the sea floor, filtering food particles from the water. Crustaceans, including crabs, lobsters, shrimp, and many other groups, were diverse and ecologically important. They occupied roles as scavengers, predators, herbivores, and feeders, and they were important items for many larger predators. The Cretaceous saw xiphactinus among the crabs, with many new families appearing during this period, and some of these Cretaceous gave rise to the familiar groups we see in the modern ocean. At the very base of the food web, the microorganisms of the Cretaceous seas were extraordinarily productive. The coccolithophores, the dinoflagellates, the diatoms, and the various bacteria and archaea that inhabited the water column and the seafloor were responsible for fixing the energy of sunlight into organic matter, for cycling nutrients, for producing and consuming oxygen, and for driving the biogeochemical cycles that regulated the chemistry of the ocean and the atmosphere. Without these microscopic organisms, none of the larger creatures could have existed. The Mosasaurs, the giant fish, the Ammonites, the sea turtles, all of them depended ultimately on the productivity of organisms too small to see with the naked eye. This is a truth that is easy to forget when we are dazzled by the megafauna of the Cretaceous seas. The great predators capture our imagination because they are dramatic, because they are large, because they fit our narratives of power and dominance. But they were the tip of a pyramid that was built on a foundation of microorganisms, and the stability of that pyramid depended on the health and productivity of that foundation. When the foundation was disrupted, as it would be at the end of the Cretaceous, the entire pyramid came crashing down. Let us now consider time itself, because the Cretaceous was not a single, uniform period. It spanned nearly 80 million years, from approximately 145 million years ago to 66 million years ago. To put that in perspective, the entire Cenozoic era, the age of mammals, the period that includes all of human evolution and all of recorded human history, is only 66 million years long. The Cretaceous was longer than the entire subsequent history of life on Earth. In that vast span of time, enormous changes occurred. Continents moved thousands of kilometers, ocean basins opened and closed, sea levels rose and fell, climates warmed and cooled, species evolved, diversified, and went extinct. The Cretaceous Oceans of 140 million years ago were profoundly different from the Cretaceous Oceans of 70 million years ago, and those were profoundly different from the Cretaceous Oceans of 66 million years ago. We tend to compress the past, to imagine it as a static tableau rather than a dynamic, ever-changing process. We picture the Cretaceous and we see mosasaurs and pterosaurs and Tyrannosaurus rex as if they all existed at the same time in the same place, in a single, unchanging world, but they did not. The world was changing throughout the Cretaceous, and the creatures that inhabited it were changing with it. The early Cretaceous oceans, still warm and still affected by the legacy of the Jurassic, were different in their species composition, their ecological structure, and their physical characteristics from the late Cretaceous oceans, which were dominated by the mosasaurs and the great bony fish and the extraordinary diversity of ammonites. This temporal depth is important because it reminds us that the Cretaceous oceans were not a single ecosystem, but a succession of ecosystems, each building on the one before it, each shaped by the specific conditions of its time. The evolutionary innovations that produced the mosasaurs did not appear overnight. They were the product of millions of years of gradual change, of incremental modifications to the body plan of a lineage of terrestrial lizards that slowly, over many generations, became better and better adapted to life in the sea. The diversification of the ammonites was similarly a long, slow process, driven by the opening of new ecological opportunities and the closing of old ones over millions of years. And yet within this long, slow process, there were moments of rapid change, of sudden disruption, of crises that accelerated the pace of evolution and reshaped the ecosystem in relatively short periods of time. The oceanic anoxic events were such moments. The radiations of new predator groups, filling niches left vacant by the decline of earlier occupants, were such moments. And the greatest crisis of all, the event that ended the Cretaceous and everything in it, was the ultimate such moment. A cataclysm so sudden and so devastating that it truncated 80 million years of evolutionary history in what may have been a matter of years. But we are not quite there yet. We are still in the Cretaceous, still swimming in the warm, shallow seas, still surrounded by the creatures that made this world so extraordinary. And there is one more aspect of this world that we need to explore before we can understand what came next. The Cretaceous connected. This seems like a simple statement, but its implications are profound. In the modern world, the continents divide the global ocean into distinct basins: the Atlantic, the Pacific, the Indian, the Arctic, the Southern. These basins are connected by relatively narrow passages, and the circulation of water between them is controlled by the geometry of those passages and by the global patterns of wind and thermohaline circulation. The result is a set of distinct oceanographic regions, each with its own temperature profile, its own nutrient chemistry, its own patterns of productivity, and to a significant degree, its own fauna. In the Cretaceous, the configuration was different. The positions of the continents, the extent of the eparic seas, and the presence of seaways between landmasses that are today connected created a global ocean that was more interconnected than the modern one. The Tethys Sea, a great tropical ocean that separated the northern and southern continents for much of the Mesozoic, was still open during the Cretaceous, providing a continuous belt of warm water circling the globe at low latitudes. This circumglobal tropical current distributed heat, nutrients, and organisms around the planet, maintaining the warm, equable climate and facilitating the spread of marine species across vast distances. The result was a degree of cosmopolitanism in the Cretaceous marine fauna that is notable. Many genera and even some species of Cretaceous marine organisms have been found on multiple continents, indicating that they were able to disperse across the connected oceans. Mosasaurs have been found on every continent, including what is now Antarctica, demonstrating their global distribution. Ammonites with their planktonic larval stages were similarly widespread. This global connectivity meant that the Cretaceous marine ecosystem was, to a significant extent, a single, integrated system. Events in one part of the ocean could affect organisms in distant parts. A disruption in one region could ripple outward, influencing ecosystems thousands of kilometers away. This connectivity was both a strength and a vulnerability. It allowed species to colonize new areas and maintain genetic diversity through ongoing gene flow between distant populations. But it also meant that a catastrophic event affecting the global ocean would have global consequences, affecting marine life everywhere simultaneously. There were no isolated refugia, no remote ocean basins cut off from the rest of the world, where populations could survive unaffected and later recolonize. When the crisis came, it came for everyone. We are now approaching the end of the Cretaceous, the moment when this entire world, this vast, productive, interconnected, dynamic marine ecosystem was brought to a sudden and devastating end. But before we get there, let us pause for a moment and consider what we have seen. We have seen a world of warm, shallow seas that covered vast portions of the Earth's surface. We have seen an atmosphere rich in carbon dioxide, a climate without polar ice, and an ocean that was warmer from top to bottom than anything in the modern world. We have seen an ecosystem without a stable hierarchy, where predators were also prey, where the balance of power shifted constantly, and where survival depended on flexibility and resilience rather than on fixed dominance. You have met the creatures that inhabited this world. Xiphactinus, the great predatory fish built for speed and ambush, swallowing prey nearly its own size in acts of desperate aggression. The Mosasaurs, those transformed lizards, marine reptiles that evolved from land-dwelling ancestors to become the most diverse and successful group of large marine predators the Cretaceous ever produced. The Ammonites, with their endlessly varied shells, their complex suture lines, their ecological versatility, their beauty. The sea turtles, the sharks, the plesiosaurs, the invertebrates, the microorganisms, each playing their part in a web of relationships so complex and so interconnected that no single thread could be pulled without affecting the whole. We have explored the sensory world of these creatures, the challenges of hunting and avoiding being hunted in waters that varied from clear to opaque, from bright to dark, from calm to turbulent. We have seen the evidence of injury and healing, the scars and fractures that testify to the violence and the resilience that characterized daily life in these ancient seas. We have considered the physical environment, the tectonic forces that shaped the continents and the oceans, the volcanic events that altered the atmosphere and the chemistry of the sea, the anoxic events that periodically disrupted the ecosystem and forced it to reorganize. And we have seen that this world, for all its dynamism and all its drama, was fundamentally interconnected, a global system in which events in one region could affect life in every other region, a system that was resilient in the face of many challenges, but that was also ultimately vulnerable to a challenge of sufficient magnitude. That challenge was coming. It was hurtling through space at the speed of a cosmic projectile, or building in the volcanic furnaces of the Earth's interior, or both. The exact mechanism is still a subject of scientific debate, but the result is not. At the end of the Cretaceous, approximately 66 million years ago, the most devastating mass extinction event in the last 250 million years struck the Earth, and the warm, rich, teeming seas of the Cretaceous were transformed, in a geological instant, into something entirely different. The event that ended the Cretaceous is associated with the impact of a large asteroid, approximately 10 to 12 kilometers in diameter, that struck what is now the Yucatan Peninsula of Mexico. The impact left a crater, the Chicxulub crater, that is roughly 180 kilometers in diameter, and that has been precisely dated to 66 million years ago, coinciding exactly with the boundary between the Cretaceous and the Paleogene periods. The evidence for this impact is now overwhelming, confirmed by multiple independent lines of evidence, including the global distribution of a thin layer of iridium-enriched clay at the Cretaceous-Paleogene boundary, the presence of shocked quartz and tektites in the boundary layer, and the direct detection and study of the crater itself through drilling and geophysical surveys. The immediate effects of the impact were catastrophic beyond anything in human experience. The energy released was equivalent to billions of nuclear weapons detonating simultaneously. The impact generated enormous earthquakes, tsunamis hundreds of meters high, and a cloud of superheated debris that was ejected into the atmosphere and rained back down on the Earth's surface, potentially igniting global wildfires. The dust and debris thrown into the atmosphere, along with sulfate aerosols generated by the impact into sulfur-rich rocks at the impact site, would have blocked sunlight for months to years, plunging the planet into a period of darkness and cold, sometimes called an impact winter. For the marine ecosystem, the consequences were devastating. The blocking of sunlight struck directly at the base of the food web. Phytoplankton, the microscopic photosynthetic organisms that produce the organic matter upon which the entire marine ecosystem depended, need sunlight. Without sunlight, photosynthesis ceased or was reduced to a tiny fraction of its normal level. The phytoplankton populations crashed. Without phytoplankton, the zooplankton that fed on them crashed. Without zooplankton, the small fish that fed on them crashed. Without small fish, the larger fish, the ammonites, and the marine reptiles that fed on them crashed. The collapse cascaded up the food web, from the base to the top, with devastating speed. But the impact was not the only factor. There is strong evidence that the Earth was already under stress in the last few 100,000 years of the Cretaceous, stressed by massive volcanic eruptions in what is now the Deccan Plateau of India. The Deccan Traps, as these volcanic deposits are called, represent one of the largest volcanic events in Earth's history, with eruptions that covered an area of over 500,000 square kilometers in basaltic lava and released enormous quantities of carbon dioxide, sulfur dioxide, and other gases into the atmosphere. These eruptions were ongoing at the time of the asteroid impact, and their effects on the climate and the oceans were significant, though the exact relationship between the volcanism and the extinction is still debated. Some scientists argue that the volcanic activity weakened the ecosystem, making it more vulnerable to the catastrophic effects of the asteroid impact. Others argue that the impact was the primary cause of the extinction and that the volcanism, while significant, was not sufficient on its own to cause a mass extinction of the observed magnitude. Still others suggest that the two events acted synergistically, with the combined effects of prolonged volcanism and sudden impact producing consequences that neither would have produced alone. The debate continues, but for our purposes, the important point is that the end of the Cretaceous was not a single, simple event. It was a complex, multifaceted crisis that involved both gradual and sudden stresses, both long-term environmental change and instantaneous catastrophe. For the creatures of the Cretaceous seas, the result was the same regardless of the relative contributions of impact and volcanism. The world they had known was ending. Shallow, productive seas that had sustained them for millions of years were becoming inhospitable. The sunlight that had powered the base of the food web was being blocked. The chemistry of the ocean was changing as acid rain, generated by the interaction of impact-derived gases with the atmosphere, altered the pH of surface waters. The food chains that had connected the smallest organisms to the largest predators were breaking down, link by link, from the bottom up. The extinction was not instantaneous for all groups. Different organisms were affected at different rates, depending on their position in the food web, their tolerance to stress, and the specifics of their biology. The organisms at the base of the food web, those most directly dependent on sunlight for their energy, were hit first and hardest. The coccolithophores suffered catastrophic declines. Many species of planktonic foraminifera, another group of microscopic organisms that are important in the marine food web and whose shells are a major component of marine sediments, went extinct. The collapse at the base reverberated upward, starving the organisms that depended on the plankton, and then the organisms that depended on those organisms. The Ammonites, those magnificent cephalopods with their endlessly varied shells, were wiped out entirely. Not a single species survived the end Cretaceous extinction. This is one of the most dramatic aspects of the extinction event, because the Ammonites had been a successful, diverse group for over 300 million years, surviving multiple previous mass extinctions, including the devastating end Permian event that wiped out over 90% of marine species. But the end Cretaceous extinction was too much. The combination of the collapse of their food sources, the alteration of ocean chemistry, and the disruption of the environmental conditions to which they were adapted proved fatal for every single species. The Mosasaurs also went extinct, completely and without exception. These magnificent marine reptiles, which had risen to dominance only in the last 30 or so million years of the Cretaceous, were gone. Their flexible feeding strategies, their adaptability, their diversity, none of it was enough to save them from a catastrophe of this magnitude. The plesiosaurs, already in decline, were also extinguished. The marine reptile dynasty that had ruled the Mesozoic seas for over 150 million years was over. The large predatory fish, Xiphactinus and its relatives, were mostly eliminated. Some lineages of bony fish survived, but the specific groups that had dominated the Cretaceous seas were largely gone. The rudest bivalves that had built the reefs of the Cretaceous tropics went extinct, taking with them the reef ecosystems that had provided habitat for countless other species. The sharks, ancient and resilient, survived. Not all species, but the group as a whole persisted through the extinction. Their conservative body plan and their ability to exploit a wide range of food sources apparently providing enough flexibility to weather the crisis. Some species of sea turtles also survived, their ancient lineage proving once again its remarkable capacity for endurance, but survival was not the same as being unaffected. The survivors of the end Cretaceous extinction entered a world that was fundamentally different from the one they had known. The warm, shallow, productive seas of the Cretaceous were gone, replaced by cooler, deeper, less productive waters. The food web had been shattered and would take millions of years to rebuild. The ecological roles that had been filled by the now extinct groups were vacant, waiting for new organisms to evolve and fill them. The balance of the marine ecosystem had been reset, and the recovery would produce a new world, with new rules, new dominant groups, and new patterns of life. This is where we will pause our story for now. We have journeyed through the Cretaceous Oceans, from their warm, shallow beginnings to the catastrophic moment of their ending. We have met the creatures that inhabited them, explored the ecological dynamics that governed their lives, and witnessed the event that brought their world to an end. In the next part of our story, we will explore what came after. We will follow the slow, painful process of recovery that transformed the shattered remnants of the Cretaceous marine ecosystem into something new. We will see how the vacated ecological roles were filled by new groups of organisms, how the sharks, the bony fish, the marine mammals that would eventually evolve, and many other groups, rose to fill the gaps left by the Mosasaurs, the Ammonites, and the other victims of the extinction. We will explore how the physical world itself changed, as continents continued to drift, ocean basins continued to open and close, and the climate shifted from the greenhouse warmth of the Cretaceous to the icehouse conditions of the modern world. And we will consider that the Cretaceous Oceans teach us about the nature of life, about the relationship between organisms and their environment, and about the forces that shape the history of the Cretaceous Oceans are gone. They existed for nearly 80 million years, and they produced some of the most extraordinary life forms the planet has ever seen. They were destroyed in a moment, a geological instant, by forces beyond the control of any living thing, but they left their mark. They left it in the chalk cliffs that line the coasts of continents. They left it in the black shales that underlie fertile farmland. They left it in the fossils that fill the museums of the world, the bones and shells and teeth and scales that tell us what once was and what was lost. And they left it in the DNA of every organism that survived, every lineage that made it through the bottleneck of the extinction and emerged, battered but alive, into the new world that followed. The story of the Cretaceous Oceans is not a story of a distant, irrelevant past. It is a story about us. It is about the world that made us, It is about the forces that shape ecosystems, that build complexity, that drive innovation, and that can, in a moment, tear everything down. It is a story about resilience and about vulnerability, about the power of life to fill every available niche and the power of catastrophe to empty them all. It is a story that is still unfolding, because the oceans of today are the direct descendants of the oceans that survived the end of the Cretaceous, and they carry within them the legacy of everything that came before. We will continue this story in the next part, taking you from the devastation of the extinction through the long recovery, the emergence of new marine ecosystems, and the eventual establishment of the ocean world we recognize today. The journey from the Cretaceous to the modern ocean is one of the most remarkable stories in the history of our planet, and it begins in the rubble of a world destroyed. But the rubble is not the end of the story. The rubble is where the next ends. There is a particular quality to silence that follows catastrophe. Not the silence of peace, not the silence of an undisturbed wilderness, but the silence of absence, of something that was there and is no longer there, of a space that was filled and has been emptied. It is a silence that carries weight, that presses against the senses, that makes you aware, almost physically, of everything that is missing. In the years and decades and centuries that followed the end of the Cretaceous, the oceans of the world held that kind of silence. Not a total silence, because life is never completely extinguished. Not even by the worst catastrophes the universe has yet delivered to this small, blue planet. But a silence defined by loss, by the absence of the Mosasaurs that had dominated every major ocean basin on Earth, by the absence of the Ammonites whose shells had littered the sea floor for 300 million years, by the absence of the great predatory fish, the marine reptiles, the reef-building rudists, and countless other organisms that had made the Cretaceous seas among the most productive and ecologically complex environments in the history of life. Please let us know in the comments where you are watching this history video and what time you are watching it, and be sure to subscribe to the channel for future videos. This is the world we inherit in the second part of our story, not the rich, warm, teeming world of the Cretaceous, but the shattered remnant of it, a world in recovery, a world in transition. A world that does not yet know what it will become, that is feeling its way forward through the darkness left by a mass extinction, that is slowly, painfully, miraculously rebuilding the complexity and the productivity that was destroyed in what may have been a matter of years. And from that rebuilding, from that recovery, would emerge something entirely new. The oceans of the Paleogene, the period that followed the Cretaceous, were not simply a repaired version of the Cretaceous Oceans. They were a fundamentally different world, governed by different ecological rules, inhabited by different creatures, structured around different food webs and different patterns of energy flow. They were, in a very real sense, the first draft of the modern ocean. But before we can understand the recovery, we must sit for a moment longer in the immediate aftermath of the extinction, because the initial conditions of the post-Cretaceous world were unlike anything the ocean had experienced in the preceding millions of years. The scale of biological loss at the Cretaceous-Paleogene boundary was staggering. Estimates vary depending on the methods used and the fossil groups examined, but the consensus is that somewhere between 70% and 80% of all species on Earth went extinct in a geologically brief interval. In the oceans, the losses were particularly severe at certain levels of the food web. The surface ocean, the euphotic zone where sunlight penetrates and photosynthesis occurs, was the most severely disrupted. This is where the phytoplankton lived, and the phytoplankton were devastated. The fossil record of marine microfossils, the tiny shells of foraminifera and the calcium carbonate plates of coccolithophores, shows a dramatic and abrupt change at the boundary. Below the boundary layer, there is a diverse, abundant assemblage of Cretaceous microfossils, the record of a productive, biologically rich ocean. Above the boundary layer, in the earliest Paleogene sediments, that diversity collapses. The dominant forms are small, simple, opportunistic species that could tolerate the disrupted, nutrient-poor conditions of the aftermath. The complex, diverse community of Cretaceous plankton was gone, replaced by an impoverished fauna of generalists clinging to survival in a world without its former productive engine. This collapse of the plankton had a specific, measurable signature in the geological record. In the sediments deposited in the immediate aftermath of the extinction, there is a dramatic decrease in the carbonate content. During normal times, the continuous rain of tiny calcareous shells from the surface ocean, the coccoliths and foraminiferal tests, accumulates on the seafloor and forms carbonate-rich sediments. When this rain stops because the organisms producing it have gone extinct, the sediment changes character. This interval of carbonate-poor sediment, sometimes called the Strangelove ocean effect, after a concept suggesting the ocean had temporarily lost its biological productivity, lasted for hundreds of thousands of years. It is a graphic, tangible record of an ocean that had lost much of its biological machinery and was struggling to rebuild it. The darkness came first. That is perhaps the most important thing to understand about the immediate aftermath of the impact. The debris and aerosols injected into the atmosphere by the asteroid impact, possibly combined with soot from the wildfires that may have swept the land, reduced the amount of sunlight reaching the Earth's surface to a fraction of normal levels. Photosynthesis, both on land and in the ocean, slowed dramatically. The precise duration of this darkness is still uncertain, with estimates ranging from months to years, but even a relatively brief interruption in photosynthesis could have catastrophic consequences for organisms that depended on it, either directly as photosynthesizers or indirectly as consumers of organic matter produced by photosynthesis. For the marine ecosystem, the darkness essentially switched off the primary power supply. The phytoplankton unable to photosynthesize died in enormous numbers. The zooplankton that fed on the phytoplankton starved. The small fish that fed on the zooplankton starved, and without fish and other small prey, the larger predators had nothing to eat. The collapse was not just from the top down, as large predators were suddenly deprived of their prey. It was from the bottom up, as the entire food web was starved of its primary energy source. A food web collapse of this kind is particularly devastating because it strikes simultaneously at every level. Even if a predator could somehow find enough to eat, its prey population could not recover without a functioning base, and the base could not recover without light. At the same time, the chemistry of the ocean was changing. The impact released enormous quantities of sulfur dioxide, carbon dioxide, and other gases into the atmosphere. Sulfur dioxide combined with water vapor to form sulfuric acid, which fell as acid rain over the entire planet. This acidification of ocean surface waters was particularly damaging to organisms that built their shells and skeletons from calcium carbonate, because carbonate dissolves in acidic water. Ammonites, pteropods, coccolithophores, and many other carbonate-secreting organisms were doubly stressed, facing both the collapse of their food supply and the dissolution of their protective structures. The synergy of these multiple stresses is what made the end Cretaceous extinction so catastrophic, and why even groups that had survived previous mass extinctions were unable to persist through this one. The temperature also changed. The initial darkening caused by atmospheric debris would have produced a rapid cooling effect as sunlight was blocked and less heat reached the surface. This cooling was superimposed on a climate that had been warm throughout the Cretaceous, and the shift would have been dramatic and disorienting for organisms adapted to stable, warm conditions. But the cooling was not the end of the temperature story. The enormous quantities of carbon dioxide released by the impact and by the continuing Deccan Traps volcanism would eventually, as the dust and aerosols settled out of the atmosphere, produce a warming effect. So the climatic aftermath of the extinction was not a simple, linear cooling. It was a complex, multi-phase sequence of cooling followed by warming followed by gradual stabilization, unfolding over thousands to tens of thousands of years, and superimposed on an ocean that had lost most of its biological complexity and was struggling to rebuild. In this context, the question of who survived and why takes on great importance, because the survivors were the seeds from which the new ocean would grow. Understanding which groups made it through the extinction and what characteristics allowed them to survive tells us something fundamental about the nature of life in crisis. It tells us what kinds of biological strategies are robust against catastrophe, what kinds of ecological roles provide a buffer against extinction, and what kinds of organisms are most likely to inherit the world after a mass dying. Several patterns emerge from the fossil record. First, organisms with resting stages, dormant forms that could survive periods of unfavorable conditions, were more likely to survive. Many phytoplankton species, for example, can form cysts or spores that sink to the bottom and remain dormant for years or even decades, waiting for conditions to improve. These dormant stages were the seeds of the post-extinction recovery, the reservoirs of biological potential that lay in the sediment, waiting for light and nutrients to return. When conditions improved, these cysts germinated, and the organisms that emerged from them began the slow process of rebuilding the phytoplankton community. Second, organisms with flexible diets, the generalists who could eat many different things, were more likely to survive than strict specialists. When the food web collapses, a specialist that eats only one type of prey has no options. A generalist can shift its diet, seeking whatever is available, even if it is not its preferred food. The sharks which survived the extinction are instructive here. Sharks are famously opportunistic feeders, capable of consuming a wide variety of prey, from fish and cephalopods to crustaceans, sea turtles, marine mammals, and even detritus. When the food web collapsed and many of their preferred prey disappeared, sharks could shift to whatever was still available, scavenging on the carcasses of the extinction's victims, consuming the invertebrates that managed to survive, and generally making do in a world that had very little left to offer a large predator. Third, organisms that lived in or near the sediment in the benthic environment of the sea floor were sometimes better positioned to survive than those that lived in the water column. The sea floor, while also severely disrupted, retained some reserves of organic matter in the form of accumulated detritus. Organisms that could feed on this material, the scavengers and detritivores that consumed dead organic matter, had a food source that persisted even after the collapse of the water column food web. This is why some groups of benthic invertebrates, such as certain bivalves, sea urchins, and worms, survived the extinction with relatively modest losses compared to the catastrophic toll taken on the water column fauna. Fourth, small body size was advantageous. Large animals require more food to sustain themselves than small animals. When food is scarce, large animals starve faster. The Mosasaurs, the giant predatory fish, the large Ammonites, all of these large-bodied organisms were at a severe disadvantage when the food web collapsed. Small organisms, with their lower food requirements, could persist on the reduced productivity that was available in the aftermath of the extinction. This is why the survivors tended to be small, at least initially, why the immediately post-extinction fauna was dominated by tiny, opportunistic organisms rather than large, specialized ones. The recovery of large body sizes took millions of years, as the food web was rebuilt from the bottom up and enough productivity accumulated at each level to support larger and larger consumers. Fifth, depth mattered. The surface ocean, the euphotic zone, was the most severely disrupted because it was the zone most directly affected by the blocking of sunlight and the acidification of surface waters. Organisms that lived deeper in the water column, below the most severely affected zone, experienced some buffering of the impact's effects. Temperatures changed more slowly at depth. Acid rain mixed downward slowly. The collapse of surface productivity took time to propagate downward. As a result, some deep sea and mid-water fauna survived with less severe losses than the surface fauna. These survivors formed another seed population from which the recovery could grow. The recovery itself was a process that unfolded over millions of years, not centuries or decades. This is perhaps the hardest thing to convey about mass extinction recovery, because human timescales are so different from geological ones. We tend to imagine recovery as a relatively rapid process, perhaps analogous to the way a forest recovers after a fire, with new growth appearing within years and a mature ecosystem re-established within decades. But the recovery from a mass extinction is not like the recovery of a forest. It is more like starting with bare rock, without even the soil microbiome that allows forest recovery to happen, and waiting for the geological processes of weathering and biological colonization to create the conditions for life to establish itself. The initial phase of recovery, in the first few 100,000 years after the extinction, was dominated by opportunistic species, organisms that could tolerate the harsh conditions of the aftermath and that could reproduce rapidly to take advantage of whatever resources were available. These were the weeds of the post-extinction ocean, the ecological equivalents of the pioneer plants that colonize barren ground after a volcanic eruption or a glacial retreat. They were not diverse, they were not specialized, and they were not the foundation of a complex ecosystem. But they were alive, and they were the beginning. The planktonic foraminifera, those tiny, shell-bearing amoebae that float in the surface ocean, provide one of the best documented records of this early recovery. Before the extinction, foraminifera were extraordinarily diverse, with dozens of species occupying a wide range of ecological niches in the surface ocean. The extinction wiped out most of them. In the earliest Paleogene, only a handful of simple, small species survived, and these dominated the post-extinction ocean for hundreds of thousands of years. Then gradually new species began to appear. The diversification was slow at first, a species here and there, each exploring a slightly different ecological niche, each adding a small increment to the growing complexity of the community. Over millions of years, the diversity built and built, until eventually the foraminifera community of the Middle Paleogene was again a complex, diverse assemblage, though composed of entirely different species from those of the Cretaceous. The Cretaceous foraminifera were gone. The new diversity was built from the survivors, from the small, simple, opportunistic species that had made it through the extinction, and then diversified to fill the empty ecological space left by the lost Cretaceous fauna. This pattern of collapse followed by a slow rebuilding of diversity by the survivors is a recurring theme in the history of life. It happened after the end Permian extinction, after the end Ordovician extinction, after every major mass extinction event in the geological record. It is a pattern that reflects the fundamental dynamics of biological diversification. Given enough time and enough ecological opportunity, life will fill the available niche space. Empty niches attract colonists and drive evolutionary innovation. Natural selection, working on the genetic variation in survivor populations, eventually produces new species adapted to the new conditions. Diversity rebuilds, complexity increases, and eventually something like a mature ecosystem reestablishes itself. But the new ecosystem is never the same as the one it replaced. This is a crucial point, one that deserves emphasis. The recovery from a mass extinction does not restore the previous state. It creates a new state, built on a different foundation, structured around different species, governed by different ecological rules. The Cretaceous marine ecosystem was gone forever. The organisms that replaced it were the descendants of the survivors, shaped by millions of years of evolution in the new conditions that followed the extinction, and they produced a marine ecosystem that was fundamentally different from what had come before. Let us trace some of the major developments in the post-Cretaceous ocean, because they reveal the mechanisms by which the new world was constructed and the forces that shaped its character. The sharks, as we noted, survived the extinction. And in the immediate aftermath, with the large marine reptiles gone and the large predatory fish mostly eliminated, the sharks found themselves in a world that was, in some respects, open to them in a way it had never been before. The large apex predator niches that had been occupied by mosasaurs and giant fish were vacant. The sharks were among the few groups of large predators to survive, and they were positioned to expand into those vacated roles. But their expansion was constrained by the collapse of the food web. There was nothing to eat at the top of the food chain if there was nothing to sustain the middle of the food chain, and the middle of the food chain was devastated. So the sharks too were reduced in the immediate aftermath to a shadow of their former diversity and abundance. Those that survived were smaller, more generalist species, capable of eking out a living in the depleted post-extinction ocean. Over millions of years, as the food web rebuilt and fish populations recovered, the sharks diversified. New lineages appeared, experimenting with new body forms, new feeding strategies, new ecological roles. Some lineages became large pursuit predators, exploiting the recovering populations of bony fish. Others became bottom feeders, crushing shellfish with their broad, flattened teeth. Others became filter feeders, a remarkable evolutionary innovation, developing the ability to filter tiny organisms from the water in a manner convergent with the filter feeding of modern whale sharks and basking sharks. The bony fish, the actinopterygians, proved to be among the most resilient and ultimately most successful groups in the post-extinction ocean. They had been diverse and abundant in the Cretaceous, and while the extinction took a significant toll, enough lineages survived to form the nucleus of what would become the most diverse group of vertebrates on Earth. The teleosts, the most advanced group of bony fish, underwent a spectacular radiation in the Paleogene, diversifying into thousands of species that filled virtually every ecological role in the recovering ocean. Modern teleosts include everything from tiny, transparent gobies to enormous bluefin tuna, from anglerfish lurking in the deep sea to flying fish leaping above tropical waves. The extraordinary diversity of modern bony fish is the legacy of the post-extinction radiation, of the explosive evolutionary opportunism that characterized the recovery phase. As the fish recovered and diversified, new predators evolved to exploit them. And here we come to one of the most significant developments in the post-Cretaceous ocean, the emergence of marine mammals. The story of marine mammal evolution is one of the most remarkable in the history of life, a story of terrestrial animals returning to the sea in a pattern that echoes, across vast stretches of time, the story of the mosasaurs before them. But the marine mammals did not evolve immediately after the extinction. They required the evolution of their terrestrial ancestors first, and the ancestors of marine mammals were among the groups that were evolving and diversifying on land in the aftermath of the Cretaceous extinction. The death of the non-avian dinosaurs had opened the land to the mammals in much the same way that the death of the mosasaurs and the other large marine reptiles had opened the sea. On land, the mammals underwent a spectacular radiation, diversifying from the small, mostly insectivorous creatures of the Cretaceous into the vast diversity of body forms and ecological roles that characterizes modern mammalian life. And some of those diversifying mammals found their way to the edges of the sea. The earliest ancestors of the whales were terrestrial animals, hoofed mammals related to modern even-toed ungulates like deer and cattle. They lived near the shores of the ancient Tethys Sea, now reduced from its Cretaceous extent but still a significant body of water, and they began to exploit the resources of the coastal ocean. Over millions of years, their descendants became progressively more aquatic, spending more and more time in the water, their limbs shortening and flattening, their tails lengthening and developing flukes, their nostrils migrating from the tip of the snout to the top of the head to facilitate breathing at the water's surface. By the Middle Eocene, roughly 40 to 50 million years ago, the first truly whale-like animals had appeared, fully committed to aquatic life, incapable of returning to land. This transition took tens of millions of years, far longer than a human can intuitively grasp, but in geological terms it was relatively rapid, and it produced animals that were fundamentally different from the marine reptiles they were, in a sense, replacing. Whales are not simply dolphins or mosasaurs in a different suit. They are mammals, warm-blooded, breathing air, nursing their young on milk, with all the metabolic, sensory, and cognitive characteristics that mammalian biology implies. The move of mammals into the ocean did not simply fill the ecological roles vacated by the mosasaurs. It created new kinds of ecological roles, new ways of being a large marine predator that had not existed before. Consider the evolution of echolocation in the toothed whales, the odontocetes. Echolocation, the ability to produce and detect sound pulses and use the returning echoes to navigate and locate prey, is a sensory modality that the mosasaurs, with all their adaptational creativity, never evolved. It is a mammalian innovation, derived from the sophisticated auditory systems of terrestrial mammals and refined over millions of years of aquatic life. Echolocation allows modern dolphins and toothed whales to locate prey in complete darkness, to detect the movement of individual fish in murky water, to navigate complex environments with extraordinary precision. It is, in many respects, a more powerful sensory tool for ocean hunting than anything the Cretaceous marine reptiles possessed, and it fundamentally changed the nature of the predator-prey relationship in the marine environment. The baleen whales, the mysticetes, evolved a different set of innovations. Their filter feeding systems, the elaborate structures of keratin that replace the teeth of their ancestors and allow them to strain vast quantities of small organisms from the water, are without parallel in the earlier history of marine life. There were large filter-feeding fish in the Cretaceous, some of them possibly quite large, but nothing that approached the scale of a blue whale filtering krill. The evolution of filter feeding in the great whales was driven by the availability of vast, dense concentrations of small prey organisms, particularly krill and small fish, which themselves were a product of the specific oceanographic conditions of the Cenozoic Ocean. Those conditions, characterized by strong upwelling driven by the new patterns of ocean circulation, associated with the cooling climate and the growth of polar ice caps, produced concentrations of nutrients and plankton that had no real parallel in the warm, poorly stratified Cretaceous seas. The baleen whales were not just new animals. They were animals that could only have evolved in the specific conditions of the post-Cretaceous world. This brings us to a crucial aspect of the post-extinction recovery that we have not yet fully addressed: the physical transformation of the ocean itself. The world that emerged from the Cretaceous extinction was not simply a depleted version of the Cretaceous world. It was a physically different world, with a different climate, different geography, different ocean chemistry, and different patterns of circulation. And this changed physical world shaped the evolution of the new marine ecosystem in fundamental ways. The continents continued to move after the Cretaceous. The opening of ocean basins that had begun during the Mesozoic continued, and new configurations of land and sea emerged. One of the most important geographical changes of the Cenozoic was the progressive isolation of Antarctica. In the early Cenozoic, Antarctica was still connected to the southern portions of the other continents by land bridges, and ocean circulation could flow around the pole. But as the continents drifted apart, first South America and then Australia separated from Antarctica, opening seaways between them and allowing ocean currents to circulate around the Antarctic continent without being blocked by land. This circumantarctic current, sometimes called the Antarctic Circumpolar Current, became one of the most powerful ocean currents on Earth, and its establishment had profound consequences for the climate of the entire planet. The The Antarctic Circumpolar Current isolated Antarctica from the warmer waters to the north, preventing the transport of heat from lower latitudes to the pole. Antarctica began to cool. Ice sheets began to form. And as the ice sheets grew, they reflected more sunlight back into space, cooling the planet further in a positive feedback loop. The Cenozoic, the era following the Cretaceous, was characterized by a long-term cooling trend that transformed the Earth from the greenhouse world of the Cretaceous to the icehouse world of the present. By the beginning of the Pleistocene, roughly 2.5 million years ago, there were massive ice sheets covering both poles and extending far into the temperate regions during glacial maxima. This cooling transformed the ocean. Cold water holds more dissolved oxygen than warm water. As the ocean cooled, its oxygen content increased, supporting a different kind of biological community than had existed in the warm, sometimes anoxic Cretaceous seas. The cooling also drove the formation of cold, dense bottom water at the poles, which sank and spread along the deep ocean floor, creating the thermohaline circulation that drives modern deep ocean circulation. This circulation pattern, often called the global ocean conveyor belt, distributes heat, nutrients, and oxygen around the world's oceans, and it has profound effects on marine productivity and the distribution of life. The establishment of strong thermohaline circulation was one of the most important developments in the post-Cretaceous ocean. It created a more dynamic, more strongly stratified ocean, with cold, nutrient-rich water at depth and warm, nutrient-poor water at the surface. But it also created powerful upwelling zones, places where deep water is brought to the surface by wind-driven divergence, carrying its load of nutrients into the sunlit surface ocean and fueling explosions of phytoplankton productivity. These upwelling zones, found along certain coastlines and in the open ocean, became among the most biologically productive places on Earth, supporting dense populations of fish, seabirds, marine mammals, and other organisms. The Cretaceous oceans, for all their warmth and extent, did not have upwelling zones of this kind, at least not to the degree that characterizes the modern ocean. Their productivity was more diffuse, sustained by the warm temperatures and the abundant nutrients recycled within the water column, rather than by the injection of cold, nutrient-rich deep water from below. The modern ocean's productivity is more concentrated, more episodic, more tied to the dynamics of upwelling and thermohaline circulation, and this has shaped the distribution of marine life in ways that are fundamentally different from the Cretaceous pattern. Consider the great fishing grounds of the modern world, those extraordinarily productive regions where cold, nutrient-rich water wells up from the deep and supports enormous populations of small fish like anchovies, sardines, and herring, which in turn support larger predators. These regions are products of the specific oceanographic conditions of the post-Cretaceous world, conditions that did not exist in the Cretaceous. The biological richness of these upwelling regions, the vast schools of fish, the teeming seabird colonies, the populations of whales and dolphins, all of this is a post-Cretaceous phenomenon, shaped by the cooling climate, the changing continental configuration, and the establishment of strong thermohaline circulation. The sea floor itself changed. The rudest reefs of the Cretaceous, those extraordinary structures built by cone-shaped clams, were gone. In their place, as the ocean cooled and conditions changed, coral reefs began to develop in their more modern form. Scleractinian corals, the stony corals that build modern reefs, had existed in the Cretaceous, but had not been the dominant reef-building organisms. After the extinction, with the rudists gone, the Scleractinian corals expanded into the vacant reef-building niche. But they did so slowly, and the recovery of reef ecosystems was one of the slower aspects of the post-extinction recovery. For millions of years, the tropical seas lacked the complex, three-dimensional reef structures that had provided habitat for so many organisms in the Cretaceous. The reef ecosystems that eventually developed were different in their architecture, their species composition, and their ecology from the rudest reefs they replaced. The seagrass meadows of the modern shallow tropical seas are another post-Cretaceous development. Seagrasses, the only truly marine flowering plants, evolved during the Cretaceous but became more widespread and ecologically important in the Cenozoic, following the extinction. These meadows, anchored in the shallow sediments of tropical and subtropical coasts, provide habitat and food for a variety of marine organisms, including sea turtles, dugongs, manatees, and a host of invertebrates and small fish. The seagrass ecosystem is a distinctly modern feature of the shallow tropical ocean, one that has no precise Cretaceous analog. The kelp forests of the cold water coasts are also a post-Cretaceous development. The giant kelps, the brown algae that build the towering underwater forests of temperate coastal regions, require cold water and specific oceanographic conditions that did not exist during the warm Cretaceous. These forests, with their complex three-dimensional structure, their extraordinary productivity, and their role as habitat for an enormous diversity of fish, invertebrates, and marine mammals, are a product of the cooling of the ocean in the Cenozoic and the specific geographic conditions of certain coastlines. They represent one of the most distinctive and ecologically important marine habitats on Earth, and they are entirely a post-Cretaceous phenomenon. As the physical world changed and the biological world recovered and rebuilt, new predator-prey dynamics emerged. The relationship between predators and prey in the post-Cretaceous ocean was not simply a scaled-down or modified version of the Cretaceous pattern. It was organized around different principles, reflecting the different body plans, sensory systems, and behaviors of the new dominant groups. The rise of the marine mammals as major predators introduced a qualitative change in the nature of predation in the ocean. Mammals, with their warm blood and their relatively large brains, are capable of complex behaviors that reptiles cannot match, or at least cannot match to the same degree. The coordinated hunting behaviors of dolphins and killer whales, which hunt in sophisticated, coordinated groups, using communication and cooperative strategies to herd and capture prey, represent a level of behavioral complexity that has no Cretaceous parallel. The Mosasaurs, for all their success, were reptiles, and while reptiles can exhibit surprisingly sophisticated behaviors, they do not form the kind of tightly coordinated social groups, with complex communication and division of labor, that characterize the hunting behavior of dolphins and orcas. This behavioral complexity changed the nature of the predator-prey arms race. Prey species evolved not just to be faster or more heavily armored, but to be smarter, more socially coordinated, more capable of detecting and evading a sophisticated predator. Schooling behavior of modern fish, the way in which vast numbers of individuals move in perfect synchrony, creating a confusing, shimmering mass that makes it difficult for a predator to single out an individual target, may have been partly driven by the selective pressure of hunting by intelligent, coordinated predators like dolphins. The arms race in the post-Cretaceous ocean was not just a race of speed and size, but a race of intelligence and coordination, of behavioral sophistication. The birds of the sea also deserve attention, because the marine birds that evolved in the Cenozoic became important predators and scavengers in the post-Cretaceous ocean, filling roles that had been partly occupied by pterosaurs in the Cretaceous. The pterosaurs, the great flying reptiles, had been eliminated in the extinction, and the ecological role of aerial hunters and scavengers over the open ocean was left vacant. The birds, which had survived the extinction as one of the lineages of feathered dinosaurs, evolved a remarkable variety of forms adapted to marine life in the Cenozoic. Penguins evolved in the Southern Ocean, losing the ability to fly in air but becoming extraordinarily capable swimmers, pursuing fish and squid with a speed and agility underwater that rivals that of many fish. Albatrosses evolved the ability to glide over vast stretches of open ocean on their enormous wings, covering thousands of kilometers in a single foraging trip. Pelicans, gannets, and boobies evolved spectacular plunge diving techniques, plummeting from the air into the sea to capture fish near the surface. Frigate birds evolved the ability to steal food from other seabirds, a lifestyle of airborne piracy that has no precise Cretaceous analog. Auks and murres evolved a lifestyle similar to penguins in the northern hemisphere, swimming underwater in pursuit of fish and crustaceans. This diversity of marine bird forms, each exploiting a different aspect of the interface between the air and the sea, represents an ecological innovation of the post-Cretaceous world. The Cretaceous had its own marine birds, the Hesperornithiforms and the Ichthyornithiforms, but they were less diverse and less ecologically dominant than the Cenozoic marine bird fauna. The post-extinction radiation of seabirds filled a set of ecological roles that had been previously occupied by a different assemblage of organisms, and it did so in ways that were distinctly avian, reflecting the specific adaptations and capabilities of birds rather than reptiles. Let us now return to the theme of ecological resilience and the nature of the new ocean ecosystem that emerged from the recovery, because it is here that the contrast with the Cretaceous world becomes most instructive. The Cretaceous marine ecosystem, as we explored in the first part of our story, was characterized by a fluid, shifting balance, without a stable hierarchy and without a fixed apex predator. Every creature was simultaneously predator and potential prey. The competitive landscape was intense and unpredictable, favoring adaptability and opportunism over specialization and dominance. The post-Cretaceous Ocean, the ocean that developed over the Cenozoic, shows a somewhat different ecology. It is not that the modern ocean has a perfectly stable hierarchy with a single, unchallenged apex predator. The orca or killer whale, sometimes described as the apex predator of the modern ocean, is a formidable hunter, but it is not unchallenged. Great white sharks, sperm whales, and other large predators each have their own ecological domains, their own prey preferences, their own competitive relationships. The modern ocean is still a complex, dynamic ecosystem with multiple top predators and constantly shifting competitive relationships. But the modern ocean is different from the Cretaceous Ocean in one important respect. The roles within it are somewhat more distinctly differentiated, more clearly carved out. The baleen whales occupy the niche of large-scale filter feeders, straining vast quantities of small organisms from the water, a niche that had no real occupant in the Cretaceous seas. The sperm whales occupy the niche of deep-diving predators of squid, diving to depths of over a kilometer in pursuit of giant squid and other deep-sea prey, a niche that again has no direct Cretaceous parallel. The dolphins and smaller toothed whales occupy the niche of fast, intelligent, coordinated hunters of fish and squid in the middle water column. These are not perfectly rigid roles, and overlap in competition certainly exist. But the broad outlines of the niche structure are different from the Cretaceous pattern, reflecting the specific adaptations and behaviors of the organisms that evolved in the post-extinction world. One of the most striking differences between the Cretaceous and modern oceans is the role of the deep sea. The deep ocean, the vast volume of water below the reach of sunlight, was certainly inhabited during the Cretaceous. But the deep-sea fauna of the Cretaceous was different from the modern deep-sea fauna, partly because the physical conditions of the deep ocean were different. The warm, poorly oxygenated deep water of the Cretaceous supported a different community of organisms than the cold, well-oxygenated modern deep sea. The periodic anoxic events that affected the Cretaceous deep ocean would have been particularly devastating to deep-sea communities, periodically wiping them out and forcing recolonization from oxygenated shallower waters. The modern deep sea, cold and oxygen-rich, supports a remarkable diversity of life, from the bizarre bioluminescent creatures of the twilight zone to the strange, slow-moving organisms of the abyssal plain. The deep sea is now recognized as one of the most species-rich environments on Earth, harboring an extraordinary diversity of invertebrates, fish, and microorganisms. This diversity is a product of the long history of the post-Cretaceous deep sea, millions of years of biological evolution in the stable, cold conditions of the modern deep ocean. It is a world that had no real parallel in the Cretaceous. The role of microorganisms in the post-Cretaceous ocean also deserves consideration, because while the large animals capture our attention, it is the microorganisms that fundamentally govern the chemistry of the ocean and the cycling of nutrients. The Cretaceous was itself a time of enormous microbial activity, with the vast chalk deposits formed by coccolithophores being the most visible legacy. But the post-Cretaceous ocean developed its own characteristic microbial community, shaped by the changed physical and chemical conditions of the Cenozoic ocean. The diatoms, a group of silica-shelled phytoplankton that had been present but relatively modest in importance in the Cretaceous, underwent a spectacular radiation in the Cenozoic and became the dominant phytoplankton group in the colder, more nutrient-rich waters of the post-extinction ocean. Diatoms are extremely efficient photosynthesizers, capable of blooming rapidly when nutrients are available. They are the foundation of many of the world's most productive marine food webs, particularly in the cold, upwelling regions where their large cells and rapid growth rates give them a competitive advantage over smaller, more slowly growing phytoplankton. The rise of the diatoms was one of the most important biological developments of the Cenozoic ocean, transforming the character of marine primary production and shaping the ecology of the organisms that depended on it. The calcareous phytoplankton, the coccolithophores that had been so important in the Cretaceous, recovered and remained significant, but their ecological dominance shifted toward the warmer, more oligotrophic parts of the ocean, the tropical and subtropical gyres where nutrients are scarce and competition for them intense. In these low-nutrient environments, the smaller, more efficient coccolithophores have a competitive advantage over the large, nutrient-demanding diatoms. The spatial partitioning of the ocean between diatom-dominated productive zones and coccolithophore-dominated oligotrophic zones is a feature of the modern ocean that has important implications for the distribution of marine life and the cycling of carbon. The reconstruction of the marine food web after the extinction also involved the gradual reassembly of the complex relationships between species that characterize a mature ecosystem. Predator-prey relationships had to be re-established, not between the same species as before the extinction, since most of those species were gone, but between new species evolving into the available ecological roles. Symbiotic relationships had to be rebuilt, as new combinations of organisms discovered ways to interact beneficially. The whole elaborate network of mutualism, commensalism, parasitism, and predation that characterizes a complex ecosystem had to be assembled piece by piece through the slow process of evolution and ecological interaction. Some of these relationships were rebuilt relatively quickly, at least by geological standards. The basic relationship between phytoplankton and zooplankton, for example, was re-established within the first few 100,000 years of the recovery, as surviving zooplankton populations expanded to exploit the recovering phytoplankton. But the more complex higher-level relationships, those involving large predators and their prey, the specific ecological dynamics that define the upper levels of the food web, took much longer. The establishment of large, complex predator guilds, comparable in their ecological richness to the Mosasaur-dominated predator guild of the late Cretaceous, took tens of millions of years. The modern assemblage of large marine predators, including the great whales, the large sharks, the dolphins and orcas, and the giant tunas and swordfish, is the product of this long, slow process of reassembly. And the process is not finished. Evolution never stops. The marine ecosystem continues to change, to evolve, to develop new species and new relationships. The whales that exist today are not the whales of the Eocene. The sharks that patrol modern reefs are not the sharks that survived the Cretaceous extinction. Over the 66 million years since the end of the Cretaceous, the marine ecosystem has been in a constant state of change, its direction shaped by the continuing movement of continents, the ongoing changes in climate, the evolutionary innovations of the organisms within it, and the interactions between them. The fossil record of the Cenozoic, while less dramatic in its megafauna than the Cretaceous, is no less informative about the dynamics of the marine ecosystem. The Great Miocene period, roughly 23 to 5 million years ago, saw some remarkable developments in marine life. The Miocene seas were characterized by a diverse and in some respects extraordinarily rich fauna, including the existence of the most enormous shark that ever lived. Odotus megalodon, commonly known simply as megalodon, was a predatory shark of truly awesome dimensions. Estimates of its maximum size based on tooth dimensions and comparisons with living relatives suggest it may have reached lengths of 15 to 20 meters, making it 2 to 3 times the length of the largest modern great white sharks. Its teeth were enormous, up to 17 centimeters in length, serrated and blade-like, capable of inflicting catastrophic wounds on the largest prey animals. And its prey, based on the evidence of its teeth found embedded in the bones of fossil whales, included the great baleen whales. Megalodon was in some respects the apex predator of the Miocene Ocean, the closest equivalent in the post-Cretaceous world to the dominant large predators of the Cretaceous seas. But even Megalodon was not unchallenged. It coexisted with large dolphins and early relatives of modern sperm whales, some of which were themselves formidable predators. And Megalodon did not last. It went extinct approximately 3 to 4 million years ago in an extinction event that is thought to be related to the cooling of the oceans, the decline of its large whale prey in some areas, and perhaps competition from the evolving orca, which was at that time beginning its diversification into a highly intelligent, highly coordinated pack predator. The story of Megalodon and its extinction is itself a microcosm of the broader story of the post-Cretaceous ocean. Large apex predators evolve, dominate for a time, and then decline and are replaced as the conditions that favored them change. The pattern we saw in the Cretaceous of successive dominant groups rising and falling continued in the Cenozoic, though the timescales and the specific mechanisms were different. The ocean is not a stable system with permanent rulers. It is a dynamic, ever-changing environment in which dominance is always temporary, always conditional on the specific circumstances of the moment. As we consider the long arc of ocean history from the Cretaceous to the present, several profound themes emerge that transcend the specific details of individual species or time periods. The first is the extraordinary resilience of life. The end Cretaceous extinction was devastating beyond anything most of us can truly imagine. It wiped out 70 to 80% of all species, including some of the most successful and diverse groups of marine organisms in the history of the planet. And yet life survived, and not just survived but recovered, diversified, and ultimately produced an ocean ecosystem of comparable complexity and richness to the one that was destroyed. This resilience is not a coincidence or a miracle. It is a fundamental property of biological systems, rooted in the astronomical genetic diversity of large populations, the adaptive flexibility of natural selection, and the ability of surviving lineages to explore and fill the ecological space left by the lost species. Life is extraordinarily difficult to extinguish entirely, and even the most catastrophic disruptions are followed, given sufficient time, by recovery and renewal. The second theme is the importance of contingency. The recovery from the Cretaceous extinction did not produce a predictable, inevitable result. It did not restore the Cretaceous Ocean, and it did not produce some ideally optimized, maximally efficient ecosystem. It produced a specific, historically contingent outcome, shaped by the specific accidents of which species survived, which evolutionary innovations happened to appear at which times, and which environmental conditions prevailed during the recovery period. If the asteroid had struck at a slightly different angle, or at a different location, or at a slightly different time in the geological history of the Earth, the outcome might have been different. If a different set of organisms had happened to survive the initial crisis, the subsequent recovery might have followed a very different path. The modern ocean is not the only possible ocean that could have emerged from the Cretaceous extinction. It is one specific outcome of a complex, contingent historical process, and it reflects the particular accidents of that process as much as it reflects any general principles of ecological organization. The third theme is the relationship between physical environment and biological evolution. The creatures of the Cretaceous seas were products of the Cretaceous world, shaped by its warmth, its chemistry, its geography, its patterns of circulation. The creatures of the modern ocean are products of the Cenozoic world, shaped by its cooling, its new continental configurations, its strong thermohaline circulation, its upwelling zones. Neither set of organisms could have existed in the other's world. The physical environment and the biological community co-evolve, each influencing the other in a complex, bidirectional relationship. The organisms modify the environment through their effects on ocean chemistry, on the cycling of carbon, on the production and consumption of oxygen. And the environment selects the organisms, favoring those best adapted to its specific conditions and eliminating those that cannot cope with its demands. The fourth theme is the centrality of the base of the food web. Everything in the marine ecosystem, from the smallest fish to the largest whale, ultimately depends on the photosynthetic organisms at the base of the food web. These organisms are the engine of the system, the source of all the energy that flows through the web of predation and decomposition that constitutes marine life. When the base collapses, as it did at the end of the Cretaceous, the entire system collapses. When the base recovers, the system can rebuild. The health of the marine ecosystem is ultimately a function of the health of its phytoplankton, and the productivity of the phytoplankton is ultimately a function of the physical conditions of the ocean, the availability of light, nutrients, and the appropriate temperature and chemistry. This is why changes in ocean physics and chemistry, whether driven by natural forces like volcanism and asteroid impacts or by other processes, can have such profound effects on the biological diversity and productivity of the sea. The story we have been telling, from the warm, shallow seas of the Cretaceous to the catastrophic end of that world and the slow, remarkable recovery that followed, is ultimately a story about the relationship between life and the physical planet it inhabits. Life does not exist in isolation from the planet. It is embedded in it, dependent on it, shaped by it, and in turn shaping it. The carbon dioxide absorbed by Cretaceous phytoplankton and buried in the black shales of anoxic events is part of the geological carbon cycle that regulates the Earth's climate. The chalk deposited by billions of coccolithophores over millions of years of Cretaceous time has influenced the chemistry of the ocean ever since. The oxygen produced by Cretaceous marine photosynthesis is part of the atmosphere we breathe today. The Cretaceous ocean is not a dead, irrelevant past. It is woven into the fabric of the living planet, connected to the present by the chemical and geological threads that link all of Earth's history. Let us consider for a moment the detail of the immediate post-extinction transition, because it contains some of the most dramatic and informative evidence for how marine ecosystems respond to catastrophic disruption. The boundary between the Cretaceous and the Paleogene, defined in the geological record by a thin layer of iridium-enriched clay, has been studied intensively at hundreds of locations around the world. What the sediment sequences above and below this boundary reveal is a story of almost instantaneous ecological transformation, of a world that was one thing, and then, within a geological blink of an eye, became something entirely different. Below the boundary, in the uppermost Cretaceous sediments, there's the rich, diverse assemblage of Cretaceous life. The complex foraminifera, the coccolithophore plates, the remnants of Ammonite shells, the teeth and bones of fish and marine reptiles. Above the boundary, in the earliest Paleogene sediments, this assemblage is gone, replaced by a dramatically impoverished community of small, simple. In some sections, there is what geologists call a disaster fauna, an assemblage dominated by a single species of tiny, opportunistic foraminifera called Gembelytria cretaceae. This species, normally rare in the Cretaceous, became suddenly and briefly dominant in the aftermath of the extinction, simply because it was one of the few organisms capable of surviving and reproducing in the severely disrupted conditions of the earliest Paleogene ocean. The dominance of Gembelytria cretaceae in the earliest Paleogene is a vivid illustration of the concept of ecological release. When the competitors and predators that normally keep a population in check are eliminated, the population can expand dramatically, unconstrained by the biotic factors that normally limit its growth. Gembelytria was not a particularly successful organism in the Cretaceous. It was outcompeted by the more diverse, more specialized foraminifera that dominated the Cretaceous plankton. But when those competitors were eliminated, Gembelytria's tolerance for harsh conditions and its rapid reproductive rate allowed it to proliferate in the empty ecological space. It was the first organism to take advantage of the vacated niche space of the post-extinction ocean, and while it did not hold that advantage for long, as other organisms evolved and diversified to fill the space, its brief dominance tells us something important about the dynamics of the immediate post-extinction period. This pattern of initial dominance by opportunistic generalists followed by gradual diversification and the establishment of more specialized organisms is a recurring feature of post-extinction recovery. We see it in the foraminifera. We see it in the larger marine fauna, where the immediate seas were dominated by small, opportunistic fish and invertebrates before the larger, more specialized predators began to evolve and diversify. We see it in the history of every major mass extinction and its aftermath. It is a pattern that reflects the fundamental dynamics of biological systems. In a world stripped of complexity, simplicity prevails. But simplicity generates opportunity, and opportunity drives diversification, and diversification reality. Given enough time, the complexity will return, though in a new form, with new players in the familiar roles. The recovery of coral reefs after the Cretaceous extinction illustrates this process particularly well. The Cretaceous reef-building community, dominated by the rudest bivalves, was completely eliminated. The Xiphactinian corals that built the Cretaceous reefs in a supporting role survived the extinction, but the reef ecosystem were gone. In the earth, there were effectively no and subtropical sea complex, three-dimensional structure that had provided habitat for so many Cretaceous species. The recovery was slow. For the first few million, the tropical seas lacked significant reef-building activity. The corals that survived the extinction were small, solitary forms, not the colonial reef-building species that could construct substantial structures. Gradually, over millions of years, colonial corals began to evolve and diversify, and the first small, simple reef structures began to appear. But a fully developed coral reef ecosystem, comparable in complexity and diversity to the modern Great Barrier Reef or the reefs of the Indo-Pacific, did not develop until tens of millions of years after the extinction. The reef ecosystem is one of the most complex marine ecosystems on Earth, and rebuilding that complexity from the survivors of a mass extinction took an enormous amount of time. The relationship between reef building and climate is another important thread in this story. Coral reefs require warm, clear, shallow water with specific chemical conditions, including the right balance of calcium, carbonate, and other dissolved minerals. The warming of the early Paleogene, driven by the continued volcanic activity and the elevated carbon dioxide levels inherited from the Cretaceous, provided conditions that were broadly suitable for reef building. But the acidification of ocean surface waters by the elevated carbon dioxide was also a stress on carbonate-secreting organisms, including corals. The early Paleogene reef recovery was limited not just by the time needed for coral diversification, but also by the challenging chemical conditions of the post-extinction ocean. As the climate began its long-term Cenozoic cooling, the conditions for reef building improved in some respects and deteriorated in others. Cooler temperatures reduced the temperature stress on shallow water corals, but also restricted the geographic range of reefs to the warmer tropical and subtropical latitudes. The modern distribution of coral reefs, confined to a band around the equator, reflects the temperature constraints on reef-building corals, constraints that became more stringent as the planet cooled through the Cenozoic. The changing geography of the continents also affected the distribution of reefs. The closure of the Tethys Sea, that ancient tropical ocean that had provided a circumglobal corridor for warm water and marine life, dramatically altered the patterns of ocean circulation and the distribution of tropical habitats. As Africa moved northward and collided with Europe, and as the Isthmus of Panama formed, connecting North and South America, the previously connected tropical ocean was divided into distinct basins, the Atlantic and the Indo-Pacific. These two regions developed separate marine faunas, as species on each side of the barriers evolved independently. Today, the Indo-Pacific and the Atlantic Caribbean have distinct coral reef faunas, with relatively few species in common, a reflection of millions of years of evolutionary separation following the closing of the Tethyan Seaway and the Panamanian Isthmus. This biogeographic differentiation is itself an important feature of the modern ocean that distinguishes it from the Cretaceous Ocean. The Cretaceous, with its more open ocean connections, had a more cosmopolitan marine fauna, with many species distributed across multiple ocean basins. The modern ocean, with its more divided configuration, has a more regionally differentiated fauna, with high levels of endemism in isolated basins and archipelagos. The tropical Pacific, with its extraordinary diversity of coral reef species, represents a unique evolutionary heritage, shaped by millions of years of evolution in isolation from other regions. The role of islands and shallow seamounts in the recovery and the ongoing evolution of the marine ecosystem is also worth considering. As the continents drifted and volcanic activity created new islands and seamounts throughout the Cenozoic, new shallow water habitats were created in the open ocean, far from continental shores. These islands and seamounts became centers of biological diversity, colonized by organisms from surrounding waters and then evolving in their isolated conditions to produce unique, endemic species. The Hawaiian Islands, the Galapagos, and many other island chains owe their extraordinary biological diversity to exactly this process, the creation of new habitat by volcanic activity, followed by colonization and evolutionary diversification. In the marine realm, seamounts and oceanic islands provide the shallow, hard substrate that reef-building organisms need to establish themselves. They also alter the patterns of ocean circulation around them, creating upwelling of nutrient-rich deep water on their upstream sides and providing concentrations of food for the larger organisms that gather around them. Seamounts are known to be hotspots of marine biodiversity and biomass in the modern ocean, and there is every reason to believe that they played a similar role in the Cenozoic Ocean, serving as stepping stones for the dispersal of marine species across the open ocean and as nurseries of evolutionary diversification. The evolutionary and ecological story of the post-Cretaceous Ocean is also, in part, a story of the sea's relationship to the land. The continents were not passive observers of the ocean's drama. They were active participants, supplying the nutrients that fueled marine productivity, shaping the circulation patterns that distributed those nutrients, and providing the coastal habitats that were home to so many species. The rivers that drained the continents carried dissolved minerals and organic matter to the sea, fertilizing the coastal ocean. The erosion of mountain ranges, uplifted by the collision of tectonic plates, released minerals that eventually found their way to the ocean, altering its chemistry. The weathering of rocks on land consumed carbon dioxide from the atmosphere and delivered bicarbonate to the ocean, affecting the carbonate chemistry of the sea and the ability of marine organisms to build their shells and skeletons. These land-sea connections are not incidental features of the Earth system. They are fundamental links in the biogeochemical cycles that regulate the planet's climate and chemistry. The long-term cycling of carbon between the atmosphere, the land, and the ocean is one of the most important processes governing the Earth's habitability, and the marine ecosystem plays a central role in this cycling. The photosynthesis of phytoplankton removes carbon dioxide from the surface ocean. The sinking of organic matter carries carbon to the deep ocean, where it may be buried in sediments and removed from circulation for millions of years. The dissolution of carbonate shells on the deep ocean floor releases carbon dioxide back to deep water. The upwelling of deep water brings this carbon back to the surface, with the atmosphere. This is the biological pump, one of the most important mechanisms for regulating atmospheric carbon dioxide levels, and it is driven by the living organisms of the ocean. The Cretaceous biological pump, operating in its warm, stratified ocean, produced different effects on atmospheric carbon dioxide than the modern biological pump, operating in its cold, well-circulated ocean. The differences between these two modes of operation are part of the reason why the Cretaceous had higher atmospheric carbon dioxide and a warmer climate than the modern world. The changing efficiency and character of the biological pump over the Cenozoic, driven by the evolution of new plankton groups, the changing circulation patterns, and the changing continental configuration, is part of the story of how the Earth transitioned from the greenhouse world of the Cretaceous to the icehouse world of the present. The story we have been telling is not merely a historical narrative, a chronicle of creatures long dead and worlds long vanished. It is a story with profound implications for our understanding of how oceans work, how ecosystems respond to perturbation, and what the history of life can tell us about the fundamental dynamics of the living planet. The Cretaceous oceans teach us that marine ecosystems can be extraordinarily complex and productive under conditions very different from those of the modern world. They teach us that the specific character of an ocean ecosystem is determined by the physical condition, the temperature, the chemistry, and those physical conditions transform, eliminating and creating opportunities. Mass extinctions, while catastrophic in their immediate effects, are followed by recovery and by the emergence of new ecological configurations that are different from but not necessarily less complex than what came before. The study of the Cretaceous oceans also provides perspective on the pace of change. The transition from the Cretaceous world to the modern world took 66 million years. The recovery from the end of Cretaceous extinction was measured not in years or millions of years. Evolutionary ecosystems are vast timescales of humans or even of human is not a source of complacency. It is a reminder of the on which biological and of the importance of those timescales when thinking about the health and the future of marine ecosystems. The resilience of life is real, and the history of the post-Cretaceous recovery is genuine evidence of it. But resilience operates on geological timescales, not human timescales. The recovery from the end Cretaceous extinction took millions of years to produce ecosystems of comparable complexity and productivity to those that were lost. The individual species that were lost, the Mosasaurs, the Ammonites, the giant predatory fish, the rudest reefs, are gone forever. They will not return. The niches they occupied have been filled by new organisms, but the filling of those niches required the evolution of entirely new species over millions of years, and the new occupants are different from their predecessors in important ways. This is what the history of the Cretaceous oceans and their aftermath ultimately teaches us. The ocean has a memory, written in its sediments, its chemistry, and the DNA of its inhabitants. That memory extends back hundreds of millions of years, to worlds utterly unlike our own, governed by different physical rules, inhabited by different creatures, structured around different ecological principles. And from those different worlds, through the agency of evolution, catastrophe, and recovery, came the ocean we know. Every creature in the modern ocean is the descendant of survivors, organisms that made it through the extinction and adapted to the new world that followed. The sharks that patrol modern reefs carry in their bodies the legacy of the Cretaceous, shaped by their own ancient lineage, but also bearing the marks of everything that has happened since. The whales that sing in the deep ocean are the latest chapter in a story that began on land, transitioned to the sea, and has been unfolding ever since in the ever-changing waters of the world. The Cretaceous ocean is not simply a chapter in the past. It is a foundation of the present. The organic carbon locked in Cretaceous shales, the calcium carbonate stored in Cretaceous chalk, the evolutionary innovations that developed in Cretaceous seas, all of these are part of the ongoing story of the Earth and its ocean. The Cretaceous is not over. It is buried, transformed, and transmuted, but its legacy persists in the chemistry of the sediments, the evolution of the survivors, and the structure of the ocean that exists today. We image of the ocean as only the story written millions of years. We have now story, shallow, teeming seas of the Cretaceous, through the catastrophic extinction that ended them, to the slow and remarkable recovery that produced the ocean world we know. It is a story of extraordinary creatures and catastrophic events, of evolution and extinction, of resilience and loss, of a living planet in constant, restless motion. The Mosasaurs are gone, their great bodies dissolved to dust and scattered across the continents in the form of fossil bones and teeth. The Ammonites are gone, their magnificent shells preserved in stone, the only record of 300 million years of evolutionary history. Xiphactinus is gone, its fossil frozen moment of fatal ambition preserved in the chalk of an ancient seabed. But the ocean is not gone. It is changed profoundly and irreversibly, but it is alive. Its currents still circle the globe. Its phytoplankton still capture the energy of the sun. Its food webs, rebuilt over 66 million years from the ruins of the Cretaceous, still pulse with the energy that flows from sunlight to plankton to fish to whale. The story continues as it has continued through every extinction and every recovery, every catastrophe and every renewal, 100 million years since complex life first appeared in the sea. The creatures of the Cretaceous oceans are gone, but they are not forgotten. They live on in the fossil record, in the sediments of ancient seas, in the teeth preserved in chalk and the bones embedded in shale, in the spiral shells collected on beaches and displayed in museums. They live on in our understanding of how oceans work, of how ecosystems are built and destroyed and rebuilt, of how life responds to the challenges and opportunities that a changing planet presents. They live on in the fascination and the wonder with which we contemplate a world so different from our own, and in the questions that world poses about the nature of life, the history of the Earth, and our own place in the long, extraordinary story of this living planet. The Cretaceous oceans were a world of superlatives, of vast warm seas, of enormous predators, of extraordinary ecological complexity, of evolutionary creativity unmatched in the subsequent history of the marine realm. They were a world where the rules of survival were different from today, where dominance was always temporary, where adaptability was more valuable than specialization, and where the line between predator and prey was never fixed. They were a world that ended in catastrophe, but that left a legacy in the geological record, in the chemistry of the planet, and in the DNA of the survivors that connects the deep past to the living present. The ocean remembers the Cretaceous, and through the science of paleontology, through the patient reading of the record preserved in stone and sediment, so do we. The story of the ancient deep is not finished. It is a story that we are still discovering, still interpreting, still being surprised by, as new fossils emerge from the rock and new techniques reveal new details of ancient life. Every new discovery adds a page to the narrative, every new fossil a new character, every new interpretation a new dimension of understanding. And so we close this journey through the Cretaceous oceans and their aftermath, not with a sense of finality, but with a sense of the vastness of the story that surrounds us, of the deep time that underlies the world we inhabit, and of the extraordinary events that shape the ocean and the life within it. The warm seas of the Cretaceous are gone, vanished beneath the weight of 66 million years of subsequent history, but their legacy endures. And in understanding that legacy, in tracing the arc from those ancient seas to the modern ocean, we come to understand something essential about the nature of the living world, about the forces that shape it, and about the remarkable, resilient, ever-changing, never-ending story of life on Earth.